T-minus 10, 9, 8,
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go at throttle up.
I cannot see the target yet, but the image is good and stable. Copy. Everything is under control. Can you see the picture? Okay, and we're getting the picture on the ground, so you mean that I don't have to tell you? Now we're at UKV, Sergey. Copy.
We temporarily received downlink television from the vantage point of the Progress spacecraft as Sergei Krikalev prepares to use the manual docking system to bring Progress on in for its connection to the International Space Station.
Sergey?
Back with that live picture from the Progress 18 docking cargo craft.
Frame. Okay, I can see the the final approach is on. How do you read, Sergey? Sergey, I can read you loud and clear. Sergey, go ahead. So far, you can use the display frame. Yeah, I'm getting the information from course. Okay. The range is 110, and the rate range is 0.4. Copy.
Progress spacecraft now 110 meters out from the aft docking port of the Zvezda service module, approaching at 0.4 meters per second.
Through 100-meter mark. Copy.
100 meters. Again, Expedition 11 Commander Sergei Krikalev guiding the spacecraft from manually operated controls in the Zvezda service module.
90 meter, 0.4, 0.43. I'm braking a little bit. The range is 83 meters. Copy. .5-meter range, 0.4 range rate. Copy. Sergey, was the command nominal? Yes, the command is nominal. We confirm that the command was nominal. 60-meter range. 0.43 range rate, copy. The roll is on and I can see the target, but without details so far. Copy.
And the visiting vehicle officer reports that the automated Coors docking antenna has been retracted. That's a nominal step in this manual docking operation. So Sergei Krikalev using controls in the Zvezda service module to steer Progress 18 toward a target at the aft end of the Zvezda service module.
.40-meter, 0.34 range rate. Copy.
Progress 40 meters away from the space station, slowing to just 0.3 meters per second.
27 meter range, 0.34 range rate. I'm braking.
25 meters out, Sergei Krikalev slowing the approach of Progress.
On prognosis, the same information on course and 0.2 range rate. I can see the target.
Sergei Krikalev reporting that he can see that small white X, the target that he will be guiding the spacecraft toward.
15 meters. Do you need to brake for a little bit? I think that you're going a little bit too fast. No, I think it's fine. Are you getting the picture? Yes. We are getting the picture, but with a lot of interference. I'm braking off it. The range rate is 0.1. Copy. The range is about 12 meters now, and the data is exactly the same on both prognosis and course. Copy. Uh, 10 meters range, 0.1 range rate. Copy. I'm switching to pulse mode for rod handle. There is a little bit of disconnect on yaw. The range rate is 0.1.
Progress just 5 meters away from the International Space Station, closing at just 0.1 meters per second.
I cannot see the target. There is a shadow. So we are over the 3-meter mark. I'm braking a little bit. I confirm the contact.
Docking confirmed.
Congratulations, Sergei. Excellent.
At 7:42 p.m. Central Time, manual docking of the Progress 18 resupply craft with the International Space Station. Commander Sergei Krikalev at the controls.
Earlier. Okay, that's done. Sergei, stand by. So now we will start deactivating Toro.
Now that the docking has been completed, there will be 7 minutes worth of engagement of hooks and latches that will firmly connect the two vehicles in a hard mate.
Sergei, you have a go to deactivate Toro. Copy. Robot is on. I'm initiating the order air. The manual control is on. Copy. I confirm that the manual control is off. The pulse mode is off, and I'm deactivating TV. Okay, I confirm that TV is off. I'm activating BPS initial.
Progress manual docking of the Progress 18 resupply craft with the International Space Station occurring over Eastern Asia with Commander Sergei Krikalev of the Expedition 11 crew, one of the most experienced cosmonauts in the world,
BPS is
successfully bringing the Progress into a manual docking.
I confirm.
This is Mission Control Houston. We are continuing to receive a replay from the Communications and Tracking Officer of images of the arrival of the Progress 18 spacecraft at the aft end of the Zvezda service module. Again, that docking occurred at 7:42 p.m. Central Time. Commander Sergei Krikalev being required to step in and take manual control of the docking of the Progress spacecraft when ground controllers were unable to uplink the final command to begin that last stage of the approach of Progress to the space station. These pictures are showing the space station view of the arrival of the Progress using an external camera on the S1 truss structure, looking past one of the radiators for the U.S. segment of the space station and one of the Russian segment solar arrays. You can see the approaching Progress just above the tip of the solar array in the upper right quadrant of your picture. These videotape replays coming to us from a tape deck on board the International Space Station being commanded by the Communications and Tracking Officer here in Mission Control. We're expecting to continue to have television coverage from the space station for another 8.5 minutes. Again, Progress 18 docked to the International Space Station at 7:42 p.m. Station was 225 statute miles above Beijing, China when that docking occurred. Within minutes of that, the hooks and latches between the two ships had been engaged and forming an apparently tight seal. Sergei Krikalev, the commander on board, was awaiting ground go-ahead from Moscow to begin the leak checks of those seals. This docking finished off a two-day trip for the cargo ship since it lifted off from the Baikonur Cosmodrome in Kazakhstan at 6:10 p.m. Central Time on Thursday. Again, this Progress ship contains some 397 pounds of propellant, 242 pounds of oxygen and air, 926 pounds of water, and more than 3,000 pounds of spare parts, life support system components, and experiments. It also has another 40 canisters used for solid fuel oxygen generation. The crew has been using those canisters at a rate of about 2 per day to maintain the oxygen levels in the space station atmosphere. They'll use another pair of those canisters tomorrow, but then with this arrival of the Progress 18 vehicle, we'll begin to use oxygen from the Progress tank starting on Monday. Also in the cargo compartment of this Progress vehicle is another digital camera that will be used by the space station crew to document the approach of the Discovery space shuttle on the STS-114 mission, still scheduled for July. As Commander Eileen Collins guides the shuttle to its docking with the space station, at about 600 feet out, she will do a backward flip of the orbiter, presenting its underside for photography by the two crew members on the space station. They'll use 400 and 800 millimeter lens to conduct several thorough mappings of the tiles on the underside of the space shuttle to document any damage that might have occurred during launch of Discovery. Again, Discovery rolled out to the Launch Pad 39B on a crawler transporter on Wednesday and is now firmly down at the launch pad and getting ready to receive its payloads. Payload canister holding the Italian-built Raffaello multi-purpose logistics module was transferred to the launch pad in advance of the shuttle's arrival. and payload installation operations began on Friday. All the connections from the payload to the status and power systems on board the shuttle are expected to be performed this weekend. Space Shuttle Discovery, if its schedule holds, will be the next spacecraft to visit the International Space Station following the arrival of this Progress 18 vehicle. Again, this video is a replay from videotape machines on board the International Space Station. Shows the arrival of the Progress spacecraft from the vantage point of one of the external cameras on the station. Progress currently is obscured in this repeat by one of the solar arrays on the Russian segment of the space station, but you can see the two Progress solar arrays on either side of the larger array in the center of your screen. Again, the Progress vehicle docked successfully at 7:42 p.m. Central Time this evening, with Commander Sergei Krikalev on board the International Space Station in manual command of the final stage of docking.
Die unbemannte Progress M53 lieferte 2,5 Tonnen Lebensmittel, Wasser, Treibstoff und andere Versorgungsgüter für die Besatzung der ISS. Diese besteht zurzeit aus einem Amerikaner und einem Russen. Beide werden jetzt die Ankunft der US-Raumfähre Discovery vorbereiten, die im nächsten Monat zur ISS fliegen soll.
Für die Zweimann-Besatzung. In einem Monat soll vom Weltraumbahnhof Cape Canaveral aus erstmals wieder eine amerikanische Raumfähre zur ISS starten.
Krieg der Welten, die Neuauflage des Filmklassikers, startet demnächst weltweit und, mal ehrlich, zumindest bei Hauptdarsteller Cruise, der bekennende Scientologe, der derzeit jede Premierenfeier für liebestolle Ausbrüche nutzt, beschleicht einen doch der passende Verdacht, dieser Mann ist von fremden Mächten ferngesteuert. Spaß beiseite, als Orson Welles 1938 den Krieg der Welten als Hörspiel aufführte, da führte die Angst vor Außerirdischen tatsächlich noch zu einer Massenpanik in den USA. Naja, die Menschheit ist abgeklärter heutzutage, oder etwa doch nicht? Fokus TV über Besucher und Besuchte aus dem All.
Sie kommen von weit her und wollen uns entführen. Wieder einmal hat sich Regisseur Steven Spielberg seinem Lieblingsthema gewidmet, den Außerirdischen. Seine neue TV-Serie Taken basiert auf einem mysteriösen UFO-Absturz, der sich 1947 in Roswell, New Mexico ereignet hat. Seitdem berichten immer wieder Menschen von Entführungen durch Außerirdische. Einer von ihnen ist Patrick. Der 24-Jährige erinnert sich an viele Begegnungen der dritten Art. Seit seiner Kindheit holen ihn nachts immer wieder fremde Wesen. Wie, weiß er nicht.
Ich habe aber eine Erinnerung daran, dass ich zum Beispiel in einem mir fremden Raum aufwache. Auf einem Tisch, und dieser Raum war in ein helles, gleißendes, gelbliches Licht getaucht, und um mich herum befanden sich mehrere dieser grauen Wesen und haben etwas an meiner unteren Körperhälfte gemacht, irgendeinen Eingriff vorgenommen. Ich bin dann irgendwie zu mir gekommen und sie sind schnell darauf aufmerksam geworden und haben, eins hat sich zu mir runtergebeugt. Und dann war ich wieder weggetreten.
Roswell 1947. Ein unbekanntes Flugobjekt stürzt über der Wüste von New Mexico ab. Erste offizielle Erklärung, es handelt sich um Teile eines Wetterballons. Dennoch munkelt man in der Bevölkerung, ein UFO mit 4 Außerirdischen ist abgestürzt. 95 der angebliche Beweis in Form eines Videos, leider eine Fälschung. Das Alien ist eine Puppe. 2 Jahre später, pünktlich zum 50. Jahrestag, lüftet die US Air Force das Geheimnis um die angeblich geborgenen Leichen, simple Crash-Test-Dummies. Für die erste große UFO-Aufregung sorgte schon in den 30ern folgendes Hörspiel im Radio.
The spectroscope indicates the gas to be hydrogen and moving toward the Earth with enormous velocity.
Der Krieg der Welten des englischen Schriftstellers H.G. Wells. 1938 versetzte er als Radiohörspiel die amerikanische Bevölkerung in Panik. Sie glaubt, dass tatsächlich die Invasion vom Mars beginnt. Am 29. Juni kommt eine neue Verfilmung des Klassikers in die Kinos. Hauptdarsteller Tom Cruise, Regisseur Alien-Fan Steven Spielberg. Die Bedrohung durch Außerirdische. Ein reines Hollywood-Spektakel oder erschreckende Realität? Professor Wolfgang Hillebrand vom Max-Planck-Institut für Astrophysik kennt sich im Weltall aus. Er beschäftigt sich auf wissenschaftlicher Ebene mit der Suche nach extraterrestrischem Leben. Der Besuch von Außerirdischen auf unserem Planeten ist für ihn ausschließlich eine Frage der Entfernung.
Im Prinzip mit unserer Technologie, die wir jetzt haben, unsere Riesenradioteleskope, können wir zumindest hinaushorchen auf technische Zivilisationen bis zu einem Abstand von vielleicht 100 Lichtjahren oder so, grob gesprochen, je nachdem, wie stark die senden. Und eigentlich können wir ausschließen, dass in diesem Umkreis von 100 Lichtjahren, in denen schon in der Größenordnung vielleicht 1000 oder 10.000 Sterne sich befinden, eine Zivilisation ähnlich der unseren agiert und existiert.
Die offensichtlich alienfreie Zone ist allerdings nur ein Bruchteil des Universums. Allein in der Milchstraße gibt es 100 Milliarden Sterne mit möglichen Planeten. Ob diese intelligente Zivilisationen beherbergen, weiß niemand. Sicher ist, dass Menschen immer wieder glauben, etwas Ungewöhnliches gesehen zu haben. Ein ehemaliger Lufthansa-Pilot berichtet.
Es hat mich fasziniert, ich habe das Licht angesehen und es kam plötzlich auf mich zu. Und zwar in einer solchen Geschwindigkeit, dass ich zunächst mal meine Scheinwerfer anmachte. Ich dachte, es sieht mich nicht. Und den Co-Piloten noch sagte, hier pass mal auf, hier kommt was auf uns zu. Und es ging alles Minuten, Sekunden, möchte ich sagen, war das Licht da und es stand ein Feuerball, möchte ich sagen. Ein Feuerball, der nicht tot war, sondern der lebte, der pulsierte, stand dann plötzlich neben mir zwischen dem linken Innenmotor und der Kanzel.
So könnte der geheimnisvolle Ball ausgesehen haben. Diese Bilder zeigen Sichtungen von Flugobjekten, die bislang nicht erklärt werden konnten. Zwar sind Fotografien in der UFO-Szene kein Beweis, aber immerhin ein Hinweis. Und damit dieser nicht auf eine falsche Fährte lockt, werden solche Fotos von UFO-Gläubigen selbst genau untersucht. Die Vereinigung MUFONCES ist eine Gruppe von Privatleuten, die UFO-Bilder auf Fehlerquellen untersucht.
Klassisches Beispiel sind eigentlich die sogenannten Linsenreflexionen. Bei den Linsenreflexionen gelangt Licht direkt in die Linse, aber nicht so, wie es sein soll, über das Objektiv normal, sondern über die Außenhüllen wird reflektiert. Und dann sieht man jetzt hier bei dem Beispiel, hier unten sind Lichtquellen, das sind jetzt irgendwelche Lampen, die reflektieren und tauchen hier oben sozusagen als Spiegelbild über die Diagonale auf. Und dann kann natürlich derjenige, der das fotografiert hat, der denkt, ah super, habe ich jetzt ein paar UFOs drauf. Ich habe hier noch ein schönes Beispiel, das sieht man hier. Da sieht es nämlich schon nicht mehr so offensichtlich nach einer Fehlinterpretation aus. Da hat man hier dieses rote Teil da oben. Und dann hat er das auch erst nachher entdeckt, der Zeuge sozusagen, und dachte auch, oho, könnte ja vielleicht ein UFO sein, keine Ahnung, was er fotografiert hat. In Wirklichkeit ist es aber hier unten einfach dieses Polizeilicht. Das spiegelt sich auch wieder in der Linse und taucht hier oben dann sozusagen mit ganz anderen Farben auf.
Fiktion oder Wirklichkeit? Das wird auch in Zukunft die Frage bei der Sichtung von unidentifizierbaren Flugobjekten bleiben, egal ob im Film oder in der Realität.
Das ist wirklich echt, oder Sir?
Eines ist sicher, die Entführung durch Außerirdische ist für Unbeteiligte nur schwer nachzuvollziehen. Selbst Zeichnungen der Erlebnisse wecken eher Skepsis als Verständnis. Hier hat Entführungsopfer Patrick seine Erinnerungen festgehalten. Patrick fühlt sich mit seinen Erfahrungen alleingelassen.
Man erkennt einfach die Situation, wenn sie stattfindet. Bei mir tritt dann meistens diese Angst auf. Ich versuche dann ein bisschen sie einzudämmen oder ich arbeite ein bisschen daran. Also die Angst ist wirklich ziemlich stark. Es kann so eine richtige Todesangst sein. So eine Angst habe ich im Alltag noch nie erlebt.
Für Frauke Zaratnik vom Parapsychologischen Institut in Freiburg sind solche Erlebnisse durchaus erklärbar. Sie vermutet hinter Berichten von Entführungen durch Außerirdische eher psychische Probleme der Betroffenen.
Ein Erklärungsversuch wäre auch zu sagen, dass Menschen, die solche UFO-Entführungen erinnern, dass die ein traumatisches Erlebnis hatten, also dass sie entweder einen Unfall hatten oder eine Gewaltanwendung erfahren haben und dass das eigentliche Erlebnis so traumatisch ist, dass es selber nicht erinnert werden kann bewusst, sondern dass anstelle dessen eine andere Erinnerung treten muss. Und da wird eben häufig auch auf diese UFO-Entführungen zurückgegriffen. Einerseits können damit Schmerzen verarbeitet, also die Erinnerung an Schmerzen verarbeitet werden. Andererseits hat man irgendwie ein Muster, um irgendwas zu erzählen, unter Umständen auch um so eine Art Erinnerungslücke aufzufüllen. Also, weil für Menschen ist es schwer zu ertragen, wenn sie sagen, ich kann mich da an gar nichts erinnern.
Einen Besuch beim Psychologen hat Patrick bislang abgelehnt. Zu groß ist seine Angst, als verrückt abgestempelt zu werden. Beistand findet er dennoch im Chat mit anderen Betroffenen.
Natalie Godwin, and thank you for joining us here at NASA's Jet Propulsion Laboratory in Pasadena, California. It's going to be an exciting 4th of July holiday as we are preparing for a daring encounter with a comet that may help scientists unlock secrets of the formation of our solar system. Right now, the Deep Impact spacecraft is about 1.5 million miles away from Comet Tempel 1. Joining us today to brief us on the mission operations, we have Lindley Johnson. He is the program executive at NASA headquarters. Rick Vermeer, Deep Impact Project Manager, Jet Propulsion Laboratory. Monty Henderson, Program Manager from Ball Aerospace and Technologies Corporation. David Spencer, Deep Impact Mission Manager here at Jet Propulsion Laboratory. And Jennifer Rocca. She is the Deep Impact Systems Engineer here at JPL. And right now I'd like to introduce the Director of the Jet Propulsion Laboratory, Dr. Charles Alacci.
Well, good morning and welcome to JPL. Looks like we're getting in the habit of having you here every few months for some another exciting event, and we kind of like it. I think we're going to keep on that trend. When in about 58 hours and I think 15 minutes or 52 minutes, we'll be attempting probably one of the most daring and the most risky mission that we have ever undertaken in space exploration. I'm sure many of you have heard the comparison. We're trying to hit a bullet with a bullet while we're watching it from another bullet. But to make it a little bit more challenging, these are very high-speed bullets. They are going at about 20 times the speed of an actual bullet, 20,000 miles per hour. At that speed, you can come from Washington to here, like I did last night, in 6 minutes, except it was much longer, last night, and you will not have any service on the plane, at that high speed. And to make it even more challenging, we'll have to impact on the shiny side, of that bullet, so we can take good pictures. And to make it even more challenging, this is the first time this is ever done. So there are no footsteps or trails for us to follow. But I can assure you, no matter what happens, we are going to have footsteps and trails for future missions, to follow, and for future generations to follow. Now, people ask me, why are we taking that risk, on this mission? Well, like every endeavor of exploration, the payoff is worth the risk. And here, the payoff will be worth the risk that we are undertaking. Because for the first time in thousands of years, instead of fearing comets, we will be able to know what they are made of. And as you know, many scientists believe that comets, which are left from the origin of our solar system, actually brought water to Earth, and with it, life, kind of evolved on our planet. So to address this kind of high-risk kind of mission, what do? We form another dream team like we did here, like we do on all our projects on Cassini, Spirit and Opportunity, and Spitzer. And then they did everything we know how to do, to be successful. So no matter what happens tomorrow, or after tomorrow, I think we feel confident that we did everything we know what to do with the best team that we could assemble, to do this mission. So fasten your seat belts and join us on this expedition of exploration. Thank you. We'll start.
Thank you, Dr. Alacci. Before we begin this news conference, just a note that coming up in about an hour, we'll hear from the scientists working on the Deep Impact mission. So this news conference is going to be talking about the mission operations. And right now we'll start with Mr. Johnson.
Thanks, Natalie. Thank you all for joining us in what we see is going to be a very exciting 4th of July weekend. We're going to get our first in-depth look at one of the most intriguing members of the solar system, the Comet. I have the first graphic here of Hale-Bopp. This is a very recent comet, very bright comet. Humans have been fascinated by comets for millennia, and part of the reason is they can be one of the brightest objects besides the moon in our night sky. So they are very apparent, and folks are able to see them. They display spectacularly long tails, and this makes them a completely unique object in the night sky. Mystics often saw them as foretellers of the rise and fall of rulers and civilizations, and their passing have been recorded quite often in human history. And we're going to hear from the scientists about why comets are important to the history of the solar system, if not human history, and why it's essential for us to look inside. Deep Impact is the latest mission of the Discovery program. These are frequent missions, cost-effective missions that we have for solar system exploration and beyond. The science team partner with a NASA Center or Space Institute, and also with an aerospace partner to build and test and fly the spacecraft. These projects are competitively selected, and they've been the source of spectacular headlines through the last few years. The Near-Earth Asteroid Rendezvous mission landed on the asteroid Eros, even though it wasn't designed to originally do that. The Mars Pathfinder mission of the little Sojourner rover on Mars. Stardust flew through the coma of a comet and is returning dust samples to the Earth this next January. The Messenger is on its way to Mercury, and we also have 2 other missions that are in development, Dawn, which will go to the main asteroid belt, and Kepler, which is going to look for extrasolar planets. But here this week it's Deep Impact. Deep Impact will provide the most detailed pictures we've ever seen of a comet. But instead of just looking at the surface of the comet, it's actually going to plunge in and blow out the material so that we can see what's inside. It's like a large-scale experiment of a geologist taking a hammer to chip at a rock to see what it's made out of. As you can imagine, the design, building, and flying of a spacecraft on this kind of a challenging mission is a very challenging endeavor. The mission team of the University of Maryland scientists, the JPL project and mission managers, and the Ball Aerospace Engineering team have done an absolutely fantastic job on the mission and getting us to this point. So let me turn it over to them to tell you how we got to this point and what to expect this weekend.
Thanks, Lindley. Good morning, everybody, and welcome to Deep Impact once again. I'm going to provide you an overview, a brief overview of the mission itself and the remaining events, and then the follow-on speakers will go a little more in depth. But first, let me start out with a little bit of our status. Right now, both the Flyby and Impactor spacecraft, all systems are nominal. We have uploaded the final products for the sequence and execution of the actual encounter events for both flight systems. The ground operations team is well trained and ready, sitting on the edge of their seats, and I'm not sure whether they're sitting on the edge more than the science team, which is absolutely excited that we finally reached this point. If I could bottle all the adrenaline that I've seen flowing in the last day, I probably wouldn't have to sleep for a year. Okay, but to get back to the mission itself, if I could have the first picture, You heard the bullet scenario, and this is basically the 317-pound copper slug that is the business end of the deep impact impactor spacecraft that will provide the cratering mass to form the crater on the comet's surface. This obviously is the main portion of the bullet that will be hitting the bullet of Comet Tempel 1. Now, to go back to a kind of a high-level overview, if we could have the first film, what you'll see here is that we launched on January 12th of this year for a 6-month journey, about 286 million miles, to meet up and place the impactor in front of the comet. The comet will overtake it. It's currently bearing down at about 46,000 miles an hour. Relative impact will be 23,000 miles. So we did this direct trajectory for a 6-month journey, and in the meantime we've been testing and preparing for the encounter. You'll see that 30 hours out we do our final maneuver to position for the release of the impactor, and then place the impactor in the comet's path and perform the final targeting maneuvers, and then it'll be overtaken to impact the comet nucleus itself. At the same time, the flyby has positioned itself with its instruments trained on the impact site to be able to see and view the actual impact and crater formation, and then it flies under the nucleus and takes a look back. We kind of now can go down a little further into that with the next film. We'll basically show you what the next 24 hours will look like. Now, as Dr. Alacci said, we're coming up on that soon, and we're going to be releasing in a little more than a day. But the flyby spacecraft will turn itself in order to release the impactor on its impact trajectory. Right after that release, the flyby, we have to slow down so that it can position itself. So it'll perform what we call a deflection maneuver, slow down, get out of the path of the comet so it doesn't impact the comet, and then train its instruments on the nucleus. In the meantime, for about 22 hours, the impactor is in free flight. It then performs 3 trajectory correction maneuvers to impact the intended site. And the flyby is now taking pictures of that impact as well as the formation of the crater and taking science on the actual debris of the comet interior that is thrown out as a result. It then goes into a shield mode as it passes underneath the comet at a distance of about 500 kilometers. And then, after flying through, it turns back around and takes a picture of the receding comet to see if any properties of the nucleus have changed or not. So that, in a nutshell, is what we're doing. Pretty exciting. And now to give you some information on the actual flyby and impactor spacecraft itself, I'll turn it over to Monty. Monty?
Thank you, Rick. On behalf of the engineering teams here at the Jet Propulsion Laboratory at Ball Aerospace in Boulder, Colorado, and our various industry partners across the country, let me just say how excited we are to actually be here at the final hours of what has been an incredible 5.5-year effort. We can't wait to see how this journey ends. Now, I've been asked to provide a brief overview of the components of our spacecraft. Now, what we have here is a quarter-scale model depicting the release of the impactor spacecraft from the flyby spacecraft as it begins its journey onto the Tempel 1 comet. From this position, the impactor spacecraft is coming out of the flyby bay and beginning its own navigation. Now, this spacecraft is fully autonomous, fully controllable. It has its own star tracker, inertial measurement unit, computer, and propulsion system to provide its own guidance and navigation into the comet itself. As it's released and on its way into the comet, it will be taking imagery of Tempel 1 all its way in. And it will be sending that imagery back to the flyby spacecraft via S-band communication. The antenna here on top of the impactor relays information to the S-band antenna here on the flyby of the images as it's going into the comet. Now, we have the potential to receive an image of Tempel 1 comet up to 3 seconds prior to impact with the comet itself. Now, the flyby spacecraft, as Rick mentioned, after it releases the impactor spacecraft, it will do a divert maneuver to get itself out of the path of the Tempel 1 comet and directly in perfect viewing for the encounter and the resulting crater formation. It will be using its two telescopes here, the medium resolution telescope, which is identical to the impactor targeting telescope that the impactor uses for its navigation, the medium resolution telescope, the high resolution telescope here, which is one of the largest telescopes to ever fly into deep space. Now, the imagery that is collected from these two telescopes, as well as the imagery that is collected from the impactor telescope, will be sent to us here on the ground via our high-gain antenna using the Deep Space Network. Now, what we have here, these two spacecraft are the armored Humvee of deep space experiments. They're smart and they're tough. We have the potential to encounter significant debris as we're flying into the coma and the tail of the comet. So we have installed debris shields on both the Flyby and the impactor spacecraft to protect ourselves from debris. We have a debris shield here that protects the optics of the high-resolution telescope. We have debris shields here along the leading edge of the solar panel as we go into our shield mode flying through the tail of the comet. And we have debris shielding up in the bay of the Flyby that protects the computer and the other electronics as we're flying through the tail. Now, the impactor itself also has debris shielding. Interleaved within the cratering mass that we saw a picture of earlier are sheets of copper that are designed to not necessarily stop the debris that we encounter, but to break it up so that there are 5 shields, and as it breaks through the shields, it will break up and disperse the kinetic energy of the debris before it can get into the electronics and navigation system of the impactor itself. But let's keep in mind the size of the debris that we can protect against. We're traveling at 23,000 miles an hour, and these shields were designed to stop particles up to 1/4 of a gram, or 1/4 the size of an M&M. Okay, now all of our models and the data we've received from previous flyby missions tells us that we're going to be fine. But certainly for the impactor, it's going to be a very bumpy ride as it gets closer and closer to the comet. Now, the navigation and guidance control system here, for these two spacecraft, we have designed, these two spacecraft have been designed to accomplish something that the best fighter pilots in our country would not be able to do. The primary challenge of this mission, two spacecraft independently locating an illuminated area on the comet, the impactor flying itself into that lit area and impacting the comet, while the flyby diverts itself out of the path of the comet and images that same lit area to watch the encounter and the resulting crater formation and debris field, is something that could not be accomplished using human reflexes and human vision. So we had to design a navigation and control system that would allow the flyby and the impactor spacecraft to perform this very intricate ballet. For the flyby, these are our 2 star trackers. And we use those for celestial navigation, using stars to determine our position in deep space, very much in the same way that sailors for 1,000 years have used stars for navigation. In addition to the star tracker, we have an inertial measurement unit on both the flyby and the impactor. It's a suite of 4 gyros that allows us to determine our position in space. We also have propulsion systems on both spacecraft, the thrusters here, and here on the impactor, as well as reaction wheels inside the bay of the flyby spacecraft that allow us to do minor pointing exercises for imaging, as well as significant trajectory change maneuvers, such as the 3 trajectory change maneuvers we have done on our way to the Temple 1 comet, as well as the significant divert maneuver we will do to get the flyby out of the path of the Temple 1. Okay, and finally, for those of you that participated in NASA's Send Your Name to the Comet program in late 2003 and early 2004, the CD that contains your name is mounted here on the structure of the impactor. Your name will be going on with us into the comet. Okay, I'd like to hand this over now to Dave Spencer, our mission manager, to discuss the current state of the flyby and impactor spacecraft.
Thank you, Monty. Well, I'm pleased to report that both the flyby and the impactor spacecraft are healthy and ready for encounter operations.
Over the past week and a half, the flight team has been busily checking all of our command products and sequences, and we've literally uplinked thousands of these commands up to the spacecraft. These commands will take us through not only nominal operations if things go right, but also if we get surprised, we've tried to put as many contingency commands up as we think we may need to be able to react to surprises. If we can have the first graphic. This is the Flyby spacecraft at the Ball Aerospace Clean Room. The Flyby spacecraft is currently in a continuous comet pointing orientation. We're taking images of the comet every 9 minutes, and those images are critical both for our approach navigation to guide ourselves into the comet, as well as to the science team's analysis of the comet behavior, its size, shape, and rotational characteristics. Just about a week ago, we did our final checkout of the impactor spacecraft. All systems checked out perfectly, and the impactor is ready for release Saturday night. I'd like to move on to navigation challenges. Deep impact is a very challenging mission from a navigation standpoint. Trying to navigate ourselves to hit the nucleus of a comet is a little bit like a baseball player trying to hit a knuckleball. As the comet approaches the sun, it becomes active. Material on the surface of the comet nucleus outgasses, and each one of these outburst events tends to change the orbit of the comet slightly, and deep impact has to react to that. So we've got our final correction maneuver prior to release, just 30 hours prior to impact. That's Saturday evening. And this maneuver has been designed to change the trajectory of the Flyby and impactor spacecraft by about 22 miles. This is designed so that when we release the impactor spacecraft, it'll be on a near-impact trajectory with the comet, allowing the autonomous navigation system in the final 2 hours to guide itself the rest of the way in. Just to go through the timeline a bit further, impactor release occurs 24 hours prior to impact, and just 12 minutes later, the Flyby spacecraft, now flying on its own, will turn and perform its largest maneuver of the entire mission. It'll slow itself down by about 220 miles per hour relative to the impactor, and also it will place its trajectory on a close miss of the comet nucleus. This slowdown maneuver will allow it to image the impact event itself and the subsequent crater formation for about 13 minutes after impact. If we can go to the animation then. And this is the impactor following separation. And just after release, the impactor will use its thrusters to detumble itself, stabilize itself, and point its camera directly at the comet. For the next 22 hours, it's pretty quiescent, but as you can see in the animation here, during the final 2 hours, it has 3 opportunities to do maneuvers, to guide itself in the last few kilometers to the comet. The first opportunity is at 90 minutes prior to impact, the second is at 35 minutes, and the final opportunity is at 12.5 minutes prior to impact. If all goes well, the impactor spacecraft will be taking images all the way in to the point of impact, sending those images back to the Flyby spacecraft, providing us with some of the most astonishing pictures of a comet ever taken. 800 seconds after the impact event, the Flyby spacecraft will turn into a protective shield mode, placing its dust shields into the dust flow. It'll stay in this protective attitude for about 30 minutes, and then it'll turn back, point its cameras back at the comet, and take some going away pictures as we depart from Temple 1. And with that, I'd like to hand it off to Jennifer Rocca to talk about how we're going to get all this data back to Earth.
Thank you, Dave. As Dave mentioned, the Encounter Approach Imaging campaign has commenced. This consists of taking up to hundreds of images each day. The campaign is proceeding smoothly, including periodic downlinks of these images to the ground. The telemetry and image processing on deep impact is similar to a space game of telephone. Our impactor spacecraft is not capable on its own of communicating directly with Earth. So images and telemetry from this craft are transmitted to the Flyby, which in turn takes its images, telemetry, and that of the Flyby and sends it down to Earth. For the Comet encounter, Deep Impact employs a strategy called Live for the Moment. The flight team, this means that we try our best to transmit the highest priority images from both Flyby and impactor before the Flyby reaches its closest approach to the comet. This allows us to capture our very best data, even if the Flyby suffers damage as it flies close to Temple 1. On the spacecraft side of our data link, I have a smaller model here, it's a little bit easier to handle. The Flyby and impactor communicate via hardline while they're still connected. This is simply a cabled connection. As the impactor is released, the Flyby and impactor begin communication via S-band, as Monty mentioned. There is an S-band antenna here on the top of the impactor, and you can see the cantilevered S-band on the Flyby. As the Comet and the impactor come closer together, you can see that the orientation allows for the communication link between two craft to maintain stability. In addition to the S-band antenna on the Flyby, we also have a high-gain antenna, not much larger than a satellite TV antenna you may have on your house, but our antenna is a little bit more sophisticated. We actually gimbal in 2 axes, allowing us to keep the antenna pointed at Earth while the spacecraft turns underneath it during encounter. On the ground side, Deep Impact is supported by the Deep Space Network, or DSN. For the 7 days leading up to encounter, we have continuous 70-meter antenna coverage around the clock. And if you'll show the first picture, this is a 70-meter antenna at Goldstone, California. There are similar antennas in Canberra, Australia, and Madrid, Spain, supporting our encounter 200 kilobit per second downlink data rate. These large antennas allow our flight team to maintain continuous communication with the spacecraft, monitoring telemetry and receiving images. In addition, if commanding is required, we can send commands at any time. However, all commands required to proceed with our nominal encounter have already been sent to both craft. Our antenna coverage for our short encounter event is absolutely critical, and so we've timed our impact to occur when there is an overlap between a 70-meter antenna at Goldstone and a similar one in Australia. In addition to these 2 prime 70-meter antennas, the DSN has provided us with 34-meter array coverage with 4 34-meter antennas, 3 of which are shown here. The 4th one is actually located 6 miles away. These 4 34-meter antennas, when arrayed together, approximate the performance of 1 70-meter station, giving Deep Impact triple coverage for encounter. Deep Impact represents the first operational use of this 4-station array for critical mission coverage. However, the 4-station configuration is similar to 2- and 3-station arrays that have been used in the past for other missions. And of course, we have tested extensively the 4-station configuration for Deep Impact, so it will be usable for us, including successful operation during an in-flight demonstration of encounter early in Deep Impact's cruise phase. As one of the flight directors for Encounter, I speak on behalf of the Flyby and Impactor flight teams when I say we are very proud of our flight system performance and operation team performance thus far. We are totally anxious to see thrilling images of Temple 1 and the Deep Impact crater for our upcoming Comet encounter.
We are going to take questions here at JPL. Who do we have first? Okay, we can get a microphone to you over here. And we will start with this gentleman here. Before each reporter, please say your name and your affiliation.
Hi, Anthony Cabrera with Space.com and Space News. The question is directed are the imagery, is it automatically programmed to continue taking, or will you be able to adjust on the fly to take different photos as needed as you get closer up onto impact?
Our images are sequenced, and so we do have nominal sequences on board that take images periodically on both Flyby and Impactor. And we have some decision points later, depending on the environment of the comet, to select alternate images, alternate imaging sequences that will adjust for the cometary environment.
Okay, if you'll give the microphone right to this gentleman right behind you.
Yeah, Mike Dornheim with Aviation Week. Could you explain the mechanics a little bit? I'm a little confused because the post-separation burn on the Flyby slows it down, yet all the imagery shows the Flyby moving forward ahead, essentially, of the impactor and looking back at it, and those seem to be contradictory. They might not be, but could you make sense of that?
Sure. Dave, you want to answer that, or you want me to take it?
Well, I think it's probably artistic license as much as anything. The divert maneuver that the Flyby performs does slow it down by 220 miles per hour relative to the impactor. So the impactor does go ahead of the Flyby. But what I think the animations are showing is that the Flyby spacecraft flies underneath the Comet. And the Comet basically overtakes the impactor, and the Flyby dodges out of the way and goes underneath and takes the images. It's got about 13 minutes to image the impact event and the subsequent crater formation.
You're basically taking a side strike on the Comet if you were to look at it from its heliocentric velocity.
That's right.
Okay.
Okay, we're going to go to Dave Furman. Dave Furman right here, right behind you. And then we'll go to Jim Eric.
Yeah, I'm Dave Perlman from the San Francisco Chronicle. Monty, at what distance will the Flyby be from the Comet when the impactor is released?
At impact release, yeah.
Well, it's moving about 500,000 miles per day, and we release exactly a day out. Yeah. So it'll be about 500,000 miles away from the Comet at the point of release.
Okay, 500,000 miles. And then the impactor is going to move. Will it remain stationary relative to the comet, so that the comet is essentially rushing toward it, or does it move, and if it has to move to adjust its own course?
No.
Because of the comet's motion, and how much motion does that involve?
The impactor definitely has to move itself into the path of the comet, and that's why we have these final 3 targeting maneuvers to allow it to do that. So all along, it's taking pictures, trying to pick out a point on the comet to target, and it has algorithms on board that allow it to adjust its trajectory so that it puts itself in the right path.
So it has 3 targeting maneuvers prior to impact, is that correct?
Yes, it has 3 targeting maneuvers prior to impact, and all 3 of those occurred just in the last 2 hours.
Okay, nice.
Okay, give it to Jim right beside him.
Hi, Jim Erickson from the Rocky Mountain News. I'm sure the scientists will be telling us a bit about the outbursts they've been seeing from the comet lately, but I'd be interested to hear from the engineers. In general, how concerned are you about this, if at all? And specifically, if one of these things happened to erupt during the last final hours as the impactor was coming in, could it affect the targeting? Could it kind of distract or fool the impactor? And also, could it affect the likelihood that the flyby will survive its pass through the coma, if you have all this stuff being spewed out?
Yeah, I'll try and answer most of those for you. I'll obviously let the science team talk to the phenomenon more in depth from a scientific viewpoint. Basically, when we first saw this outburst, we obviously wanted to know if that represented a problem for us from a mission viewpoint, and have since determined that the overall impact of that is pretty minimal. Pretty much per prediction, this was predicted that it would occur about once every 4 to 5 rotation periods. We had another outburst early this morning per that prediction, which means that if you follow that and assume everything's going to stay relatively stable like that, then we won't have another one while we're performing the final 2 days of this. Now, having said that, also from the light curves, we see that the brightness increase is still only 20% of that of the nucleus, so we don't expect that that'll impact our optical navigation appreciably. Finally, you asked about danger to the flyby. We can only guesstimate at that. That depends on how much of an outburst, how violent it is. And as we fly under it at the 500-kilometer distance, there's a possibility that it could put some more particle debris out there, but it's nothing that would make us change our mission profile.
On the 20%, are you saying that injected brightness increases the overall brightness?
It only represents about 20% of the brightness of the nucleus.
Which is not enough to divert the impactor.
We don't believe so.
Okay. Okay.
KBC TV.
Go ahead.
My question has 4 simple parts, I think. Will we be able to see the impact with the naked eye? If so, in what direction should we look? At what time? Well, I guess that's 3 parts, if you can answer those.
No, you won't be able to see it with the naked eye, most likely. Actually, what we encourage is that you have a medium power telescope to view this from. And we say that it's mostly viewable from the western, southwestern part of the United States, maybe part of Arizona, but mostly California, over to Hawaii and New Zealand. We expect that the flash, the impact will be very momentary, so you need to be trained on that comet at the time. Obviously, we expect the observatories that we have orbiting, they're observing this as well as on the ground to see it because they'll be watching for it.
In what direction should the person with the telescope look?
Oh, I'm probably not the astronomer to get
to the southwest, the constellation of Virgo.
Close to Jupiter.
Oh, close to Jupiter, right.
Okay. We have a question in the back.
To either Monty or Dave Spencer, Pete Demetrio at KFWB Radio in Los Angeles. Question concerning the composition of the impactor and the choice of copper involved rather than a denser metal that might have gone deeper, something like tungsten or osmium. Was there a reason why that was chosen? And realistically, do you have any expectations or a range on the depth the penetrator might actually reach on the comet's surface, depending upon its composition and depending upon the speed?
Okay. Yes. The science community, when they approached us with doing this mission, told us that they would like the impactor to be made out of as much of a noble metal as possible. And that leaves us with gold, silver, or copper. And obviously, from an expense point of view, we chose copper. The rationale there is, and I'm sure Mike will speak at this later at the science briefing, is that the noble metals are not anticipated to be within the comet, and they're easily extracted out from the spectra as they're pulled out. So they encouraged us to use as much copper as possible in the impactor itself, including the entire cratering mass. Yes. Yeah. Putting in material that they know they can extract out and they don't expect to see as pristine material in the comet itself.
Depth of impact.
Well, that's the big mystery of this entire mission, is nobody knows what the crater formation is going to be. The range from bouncing off to craters the size of a standard football stadium, 100 yards long by 7 stories deep. They range, including punching all the way through. So nobody knows, and that's the point of this mission.
Okay. Yeah.
Gary Robbins of the Orange County Register. If some unforeseen problem develops with the auto nav system on the impactor, can ground controllers take over control and guide it into the comet?
Let's see. That's kind of a tough one to answer. I think the short answer would be no. We could not control it in real time from the ground. We could choose based on some of the performance behavior early on after release. We are monitoring the performance of the ADCS, the attitude control system, and also looking at the telemetry that we're getting back. We do have a couple of contingency options for deleting the first impactor trajectory maneuver if we feel that that's a value-added item. But really after that, there's not much we can do from a ground viewpoint to change the sequences that we have on board and have tested. The only logical other step you could take would be not to perform any ITMs, and in that case, your percentage probability of being able to hit the nucleus is pretty small.
Okay. We have a question here, and then we'll go over on this side. NHK?
Hi, I'm Hiro with NHK. Impactor and the Flyby will be taking many images. Are there priorities on what images get sent back first?
Yes, there are.
And what are the priorities?
They have been selected by the science team. So all the imaging campaign was designed by the science and optical navigation teams for various purposes. And included in that input to us was priority on each of the images involved in that campaign. And the highest priority images are downlinked first. So they get downlinked as soon as they're taken.
Dave Spencer mentioned the contingency sequences that have been uploaded to the spacecraft for surprises. What potential surprises might you encounter, and what's your biggest worry?
We've got a few different contingency scenarios that we've really developed fully. One is what happens if the impactor doesn't separate. Okay, we're planning on separating the impactor Saturday night and then doing our divert maneuver. If it doesn't separate, we're going to retry the separation. That will actually occur autonomously on the spacecraft. Then we'll send ground commands to try to separate. If none of that works, we've decided that we're going to take the entire spacecraft, both the mothership as well as the impactor, and impact the comet that way. That'll provide us with fantastic images on the way into the comet. And also we've got an armada, really, of spacecraft orbiting Earth, as well as the ground-based observatories taking images of this impact event. So we'll still get a lot out of that. A couple of other contingencies we have. The comet nucleus is only becoming visible to us right now. We don't know whether it's going to be brighter or dimmer than what we've assumed all along. So we have alternate sequences on board that have different image settings and image sequences to accommodate a brighter or a more dim comet.
Any other questions here at JPL? Yes, we have one in the green chair.
Gina Kim, KNBC. I have a two-part question. One, is it possible, or is there a percentage where it is not possible that it won't hit the crater at all? And If not, well, let's say it does hit the crater, then what are the chances that it won't hit the nucleus? And if so, will the experiment be a total waste, or will you still be able to get something out of that?
That's a good couple of questions. First off, I guess what I would say is I don't really use percentages when we talk about the probability of impacting the nucleus or not. Those percentages are really based only on as good as the models are that we have of the comet itself. So what I can say to that is we have used various models of comets and used those to develop our algorithms to actually get there and perform the hit. Now, what we've done is vary parameters within those models and use those variations to test our system to see which parameters and variations that we are sensitive to. And then we've gone back and adjusted our sequences so that they aren't or are less sensitive to those parameters. So we think we've covered a broad spectrum of possibilities. But in the end, as everybody said, we still don't know what this comet holds in store for us. However, we think given that testing and pushing on the boundaries that we have a very high probability of being able to impact the nucleus. Now, I think the other part of your question was, will it be, what science will we get if we have a miss of the nucleus? We're actually still in that case going to get very good, better, probably up to 10 times better, I think is how Dr. Ahern likes to put it, resolution of the comet nucleus itself than's ever been had before. And so we'll obviously get a lot of science still from the instruments as they're taking the picture in the flyby.
And if I can ask one more question, when was the last time something like this you guys have attempted something like this? And if not, then what is something similar that you could tell us about that's similar in difficulty level?
Whoa. Well, we never have attempted this. This is first of its kind event, which makes it challenging and exciting all at the same time. Now, what we can say is that we've done some similar auto navigation and optical navigation work in this area that was executed on both Deep Space One as well as the Stardust flyby of Welt 2. And so kind of that's a third generation that we've kept building on. We've never attempted something this difficult. What was the other part of your question? I'm sorry.
Well, yeah, anything similar that you can compare it to. I think you did answer it.
Okay.
Did you want to comment? Okay. Any other questions here at JPL? Okay. Hi, I'm Natalie Godwin, and thanks again for joining us here at NASA's Jet Propulsion Laboratory. It's going to be an exciting 4th of July here for us here at JPL. We're about 2.5 days away and 1.5 million miles from a daring encounter with a comet. And it may help scientists unlock the secrets of the formation of our solar system. Joining us today to tell us more about the science of this mission, we have Tom Morgan. He is the program scientist at NASA headquarters. Don Yeomans. He is the co-investigator of the Deep Impact mission here at JPL. Mike Ahern. He is the principal investigator of the Deep Impact mission, and he is with the University of Maryland. Jessica Sunshine. She is the co-investigator of the mission. She is with Science Applications International Corporation. And we have Pete Schultz. He is also a co-investigator, and he is from Brown University. And we're going to start with Tom Morgan, program scientist.
Well, thank you, Natalie. I'd like to go to the first graphic, please. This is courtesy of the Spitzer Space Telescope. We want to start by taking you back about 5 billion years to an early sun. It's not there.
We're going to try to get it.
Okay.
We're going to try one more time. We're going to try again.
Well, 5 billion years is a long time.
Okay. There you go.
There we go.
There you go.
And it's surrounded by a disk of gas and dust. And what this graphic is going to show you is the process by which water and other volatiles condense out of this gas and begin to form crystals, and the crystals collide and adhere and begin to form larger and larger bodies, and as we go along here, they will form what scientists call icy parent bodies. We have to wait a second, and there they are. Most of these icy parent bodies were swept up in the tumultuous process which formed the planets, particularly Jupiter, Saturn, Uranus, and Neptune. These objects also are believed to have contributed water and other volatiles to the Earth's atmosphere and ocean, and some people believe that complex organic molecules from the comets were part of the process which led to early life on Earth. There is a small remnant of these objects preserved from the early time to this day, and we see them every time we see a comet in the sky. We're here today to talk about an historic visit by humankind to one of these objects, Comet Tempel 1. And I will turn to my colleague here, Don Yeomans, to tell you what's so exciting about Tempel 1.
Thanks very much, Tom. As Tom pointed out, comets are important because they represent the bits and pieces from the solar system formation process. So they all formed about the same time, 4.5 billion years ago. But some of them age more quickly than others. Some of them remain in the outskirts of the solar system at the very edge of our solar system, and so they don't age very quickly. But some others, like our comet, come into the inner solar system, pass by the sun frequently, lose much of their volatiles, and approach middle age. And our comet's approaching middle age, although it's having a bit of a midlife crisis of late, and Mike will get into that. So the first slide shows an example of a fairly youthful comet. It's Hale-Bopp, and it gives the anatomy. The coma or atmosphere of a comet is the material that vaporizes from the icy nucleus, and the entrained dust particles come up, and the particles are blown back in the anti-solar direction as a result of the radiation pressure of sunlight. The ions or the gas are blown back in a gas tail because of the high-speed stream of charged particles from the sun. And buried down there in the atmosphere is the nucleus. Now, Mother Nature plays tricks on us because when the comet is distant, way out in the solar system, and there's no atmosphere to obscure the nucleus, we can't see it. It's too far away. Now, the comet comes barreling into the inner solar system and gets close enough for us to see it, but Mother Nature starts throwing up clouds of gas and dust, and so we can't see it then either. So the only way to get to these comet nuclei is to get to the spacecraft. And we have, the next slide shows the results of 3 missions. One took place in March of 1986, of course. The Giotto spacecraft from the European Space Agency went quickly past Comet Halley. And in planetary science, better resolution is better. So for Comet Halley, we have a resolution of 100 meters. That means you can see on the surface of the comet an object the size of a football field, for example. And when the Deep Space One spacecraft flew quickly past Comet Borrelly in 2001, the best resolution on our cameras then was about half a football field. And more recently, when the Stardust spacecraft flew past Comet Welt 2, the best resolution was a quarter of a football field. Well, our mission, the Deep Impact, is going to resolve objects on the surface about the size of the football. So we're making a huge leap forward in resolution, and that's good. Now, our comet, Comet Tempel 1, as I said, is a mature comet, slight midlife crisis. It could be described succinctly, perhaps, as a jet black, pickle-shaped, icy dirt ball the size of Washington, D.C. But of late, it may have a bite out of the pickle, and so the shape is going to be extremely interesting. We know that. We don't know exactly what the shape will be, but we do know it's going to be very interesting. And my final slide pays homage to the discoverer of this comet. Ernst Wilhelm Liebrecht Tempel discovered the comet back in 1867. You can see them there in its formal attire. It used to be astronomers observed the heavens in their formal attire. That's not the case any longer. However, I will note as my final note that I just want to make the point that many great astronomers sport a full beard. And with that, I'll pass it on to the principal investigator, Micah Hurd.
Thanks, Don. When we put the science team together, we seriously considered requiring all members of the science team to have full beards. We ended up getting a quarter of them to be named Mike, I think. But we had a gender equality problem, and actually if you look in that part of the room, you'll see that a large fraction of the science team, in addition to Jessica, is not of the type to have full beards. And if you, at the end, feel free to talk to the science team. They're the ones that do all the work. I sit and listen to what they're doing. So where are we now? As you heard from Natalie, we are still quite far from the comet. We're closing very rapidly, but we're still very far away. But we're already getting great scientific results out of the mission. And the first video is a clip that we released a few days ago of an outburst that happened on June 22nd. These appear, we've known for a long time that comets have outbursts, but we don't know what drives them. And this is one of the very few occasions when we've had continuous monitoring of a comet, both with imaging and with spectroscopy, and we can begin to understand the mechanism that drives these. And apparently the ones that come from Temple 1 are little ones, sneezes, puffs of smoke. They come out very quickly and dissipate. You heard in the engineering conference there was another one just yesterday morning. Very short, not much stuff came out, and it dissipated very quickly. So we're beginning to understand it, and then the next still shot actually shows some of the processing we're doing. Tony Farnham at Maryland did some really heavy processing on the images so that we can see how fast the stuff moves out. And you can see the coma expanding rapidly over the course of half a day. With a normal display of the images, the coma would not even be visible. He subtracted an average comet, so you can't even see the comet in the pre-impact image on the left-hand side. Then you see the outburst at the nucleus, and then you see the stuff dissipating. It dissipates fast enough that there is no issue for spacecraft hazard at all. So we're getting great science now, but what are we going to get when we actually get to the comet? That's, of course, the whole point of the mission. The next still shows the instruments on the spacecraft. You can also see them on the model over here and in the previous spacecraft, Monty Henderson. The previous press conference, Monty Henderson told you a bit about them. That's a scale model. The instrument is huge by interplanetary standards. That high-resolution imager is as big as I am. Small compared to Hubble, but huge compared to things that were on Cassini and Galileo, for example. So what are they going to be doing? The next video shows you what may happen. The impactor goes in, reproduces the Ranger series of images that we had on the moon several decades back. And the flyby is watching what happens. Now that's an artist's conception of what might happen, one of many possible physical scenarios. We know so little about the nature of comets that we really can't predict what the impact phenomena will be. You can't afford to send a spacecraft that has on board all of the analytical techniques that might be relevant to studying an unknown phenomenon. So in addition to observing from the flyby spacecraft and from the impactor, we're also observing from the Earth. We're using a variety of Earth orbital facilities, some of which are shown in the next still, Hubble, Chandra, Spitzer. We're also using a worldwide network of ground-based observers, and the distribution is shown in the next slide. The little red dots represent where all the key observers are, both professionals and amateurs. We have every large telescope in the world dedicated to this program, optical telescopes, radio telescopes. Key ones are in the southwestern U.S. and in Hawaii, because they're the ones that can see the impact itself. From other sites, either the impact happens in daylight or the comet's below the horizon from your particular site. But we think the events will actually unfold over days, so we need a worldwide distribution of observers to study the evolution of the comet after the impact and to understand what the steady state was before the impact. So we'll now go on and talk a little bit about the details of what we might see, and Jessica will tell you about the spectroscopy and what we hope to learn.
Thanks, Mike.
In addition to the visible instruments that we carry on Deep Impact, we have an IR spectrometer which provides us critical compositional information about the whole Comet system. And it works by breaking up light into small wavelengths or colors. And if I could have the first slide. This is a familiar concept, I think, to most, that you can break up white light through a prism into visible rainbow from red through violet. Our particular spectrometer works in a very similar manner, except the wavelengths we detect are at longer wavelengths than red. It's called the infrared. We can't see them visually, but our instruments can. And instead of a few colors, we have almost 1,000 different colors that we're going to be looking at, or wavelengths. Other instruments that Mike alluded to, for example, the Hubble Space Telescope, and actually some of the instruments on the Rosetta, will be looking at shorter wavelengths in the ultraviolet. And the reason we do this is that materials have specific responses that in these different wavelengths that we can link to what they're made out of. And if I go to the next slide, please. First of all, on the left is a visible image taken on June 20th of the comet from the medium resolution imager. And this represents the first time we were able to see anything from the spectrometer. I know it looks like squiggly lines to most of you on the right, but to those of us who've been planning this for nearly 10 years, it was very exciting to see anything, and was particularly exciting when we were able to identify, even at 10 days before encounter, clearly in the presence of materials. And what you're trying to focus on is the peaks and valleys that you can see in that graph, and we can identify water, complex hydrocarbons, CO2, that is carbon dioxide, and CO, carbon monoxide. And what was refreshing is, if you look at the next slide, please, we can compare to what we've seen previously up close from a comet, and that is nearly 20 years ago from the Vega mission to Halley. And you can see just visually that we're seeing almost the same kinds of materials in both instruments, but the really nice thing is we were 300 times farther away from Temple 1 when we took our data than when Vega took this data at Halley. So the spectrometer is working very well, and I can tell you that at this point, as of last night, we're getting signals that are on the order of 50 times brighter and clearer than what you see here. What we do with this information, I'm going to get to in a moment, but I wanted to mention the outburst that Mike talked about. We were able to observe that with the spectrometer, and from looking at the data, we were able to tell that water in the outburst was double what had been prior and what it returned back to during the outburst. And those are the kinds of things we're going to be looking at as we move forward. So if I could have the next slide, please. What we're really trying to do in understanding the composition is to understand the comet system as a whole. As Don explained, we mostly see from telescopes the outer coma or the atmosphere, but what we know is that that's not actually the material that came out. The materials that come out from the comet, which we call primary or parent materials, tend to be short-lived. They react with each other, and they react with solar radiation, and different materials are formed, and it is those secondary materials that we watch from the ground and from far away. Well, our spacecraft is going to get close enough that we'll be in the inner coma, and we'll be able to see with some detail the primary materials as they come out. So that gives us right away, coming in, a link to what we can observe before and after from the ground to what we can observe from the spacecraft. And then, of course, as a geologist, the fun part is we get to see the nucleus. We'll have data on the nucleus at unseen resolution that'll give us an opportunity to understand what that black stuff on the outside of the pickle is, and hopefully in some of the fresh areas see some perhaps fresh ice and even some rock materials. So then, of course, the reason we're doing this, the impact. And if I could have the next slide, please. What we're trying to do is see materials that were on the inside. And quite frankly, what this is like any good geologist, we take our hammer and we hit it to find out how strong it is and what it's made out of on the inside. And so this is a little experiment that Pete did for us, and he's going to explain a little detail later how it was done. But we started with a dark surface in the upper left. That surface is made of ash or soot, if you will, and underneath it we put some bright materials which represent fresh ices. And you can see during the actual impact, the material, the debris that's coming out, or the ejecta, is actually white. We've already lost, at this point, the dark materials, and we're seeing the inside of the crater. and the inside of the comet. And literally, these materials have not seen the light of day in 4.6 billion years. That's what we're waiting to see. Now, what's very exciting is that, as you can imagine, when you hit this thing, the materials that come out first come from the near surface, and over time we get things from deeper and deeper. So these materials are going to pass in front of the spectrometer, and we'll be able to see the compositional variation on the inside of the comet from watching the ejecta. Afterwards, if you can go back for the slide for one more time, in the lower right you see that the materials that were ejected at the end are now on the top. We call this inverted stratigraphy, and so when we're done, we get to look at the final crater and see that the materials that were deepest are now on the top. So I'm rather fond of our impactor, our geologic hammer, and I'm going to pass the proverbial geologic hammer to Pete.
Thank you, Jess.
Sure.
Well, I really think it's much more like a cosmic shovel.
Granted.
My students call me the Master Blaster, and so I think that's what I want to tell you about today. I do experiments. I use a variety of different types of projectiles to simulate what we might get. Now, it's interesting. We know what our projectile is. We know our probe is heading into the comet. We know what speed it is. We know how big it is, but we don't know the nature of the crust of the comet. And that's why we try to do experiments. And so our strategy is really to explore the various options. For example, it's not just the crater that we see at the end, it's also the way the material comes out of the comet itself. We even want to look at the initial flash. All these things are what we get into. Now, if we can take a look at that first time step, what we do is experiments with a large gun. It's called the Ames vertical gun range. This is 3 stories high, allows us to fire bullets or pellets, BBs if you will, about 4 miles per second. The fire gun, the chamber is about 14 feet high, 12 feet wide, and allows us to get things going so fast that there's very little left of the projectile itself. And what I want to do today is to describe 2 different scenarios, extreme scenarios, to give you a sense of what might happen. The first one is going to be sort of a pockmarked simulation to show you what happens if we have some irregular topography on the surface. And this is a case where we use loose material where there's little strength between the particles, and so if we're going to have that first time step. So don't blink, keep watching. It's going to come in from the upper right. This is a 60-degree impact going 4 miles per second. And you'll notice that immediately the first stages are extremely rapid. Then we see this conical curtain just marching its way out from across the surface. This really is trying to simulate what happens if the surface of the comet is made up of particles of dust and ice very poorly bound together. Now the second case is a little different. This is what happens if we have a crust, which is one of the likely scenarios. And this crust could develop as the gas and dust escape, and it leaves behind sort of this crust of dust and carbon compounds. Now, this particular scenario was made with a recipe for a comet. It involved some dry ice, some water ice, mixing in some dust, a little bit of window cleaner to give us some of the nitrogen, and finally a dash of Worcestershire sauce. And we put all this together, made sort of a pizza out of it, put it on top of this very high porosity material underneath, and you'll see what we get in the next time step, the next video I think I show. And you have to watch this very quickly, because you'll let you see, you saw that big flash, not so big, but you notice that there's a small hole right in the center. That hole is a strength-controlled crater, much smaller. But when that projectile goes down, when the probe goes down deeply, the whole thing begins to expand and blow out. And as a result, we see these large plates that rotate and revolve as they're thrown out. If we're able to see something like this on the comet, we should be able to determine the gravity of the comet that would then allow us to determine the mass and the density. So this is sort of our fluffy model. We hope that, in fact, this will not just uncap the comet, it will also uncork the comet. And if that's the case, then we'll have a lot to watch for. So let me end with the next time step. At the moment of impact, we will see a really bright flash. This is a flash that you won't be able to pick up. It happens within about 50 millionths of a second. Now, even though we can't see that, if we keep our eyes open, we can. And this is kind of the same for deep impact. What we will find, what we'll see, is something that perhaps lasted maybe a 60th of a second or so, extremely brief. But even though we can't see that moment of the flash, we will be able to capture it with some of the cameras. It's much shorter than a second. So what we'll see from the actual deep impact encounter, I think first thing we'll see is that flash. Next thing what we'll see is this ball of gas coming up out of the comet, and then we'll see it kind of fade, disappear, and hopefully we'll be able to begin to see the crater inside. And as that fades, we'll be able to look at the ejecta just as Jessica described. So one of the things that I do, since I'm an experimentalist, I'm always prepared for surprises. Every time I do one of these experiments, I am surprised. And I think that's the best case scenario, that for this particular experiment, we will be surprised. And so with that, I'll hand it back.
Okay, thanks, Pete. Any questions here at JPL? Okay, we are going to start with Gary Robbins, right here in the front.
Hi, Gary Robbins of the Orange County Register. Could you talk more about the connection of water on the comets with water on Earth?
On you or me?
Well, okay. Yeah, the issue is, did comets bring to the early Earth much of the water and the carbon-based molecules that allowed life to form? One of the ways you can look at that is to study the hydrogen to deuterium ratios in comets and seawater and compare them. And there isn't a complete match between the few comets that we've observed to date, but we haven't observed that ratio in short period comets, which would be most likely to impact Earth. So from my point of view, I don't know how you can avoid having comets bring water to the Earth. I mean, that's in the early solar system, the impact rate was 1,000 times what it is now. So I think in some sense it's pretty well certain that we are in fact made up of cometary stuff.
Go ahead.
Oh, I'm Dave Perlman from the San Francisco Chronicle. I've got two questions, one for Dr. Sunshine and one for Michael Hearn. And maybe Dr. Sunshine first. Pete Schultz showed us a graphic of what might happen if the impact actually craters and releases crustal material. Can the IR spectrometer analyze that in any way so that you get a picture of what the compounds are in that crustal material? Because that's rocky stuff and might tell you a lot more than just the atmospheric stuff.
Yeah, actually our spectrometer was designed specifically to do both the coma, the atmosphere, and the geology. And the wavelengths we chose are very good for seeing the gases that I talked about, as well as ices, but also hydrogen carbon-bearing materials, tars and things, but also silicates, which are the rock-forming minerals. So if it's there, we'll be able to see it. It's going to be quite a challenge to unravel all those things that are probably going to be occurring all at the same time, but we'll get it.
Well, that's great. And for Michael Hearn, if I may, you said great science from what's been seen of the, I guess, 3 eruptions now, 3 brightenings of the coma. Could you tell us what the great science is?
I think for the first time we have a chance to choose among the dozen or so ideas that have been propounded in the literature to explain cometary outbursts. The ideas include, for example, that the outbursts are due to impacts, natural meteorite impacts. They must occur. They have included transitions of amorphous ice into crystalline ice. They have included a variety of other things. And by looking at the changes in chemical composition in a natural outburst, I think we will be able to pin down which of these many mechanisms is responsible. We're also learning that these small outbursts are, in my view, more common than we had realized before, these sneezes or puffs, because these just aren't typically caught unless you have a very intensive observing program, which we don't have for most comets.
Any other questions here? Okay, Jim Erickson? Right there.
Jim Erickson from the Rocky Mountain News. Just a point of clarification. I think in the previous briefing, somebody said that the latest outburst happened yesterday morning. Was it yesterday or he said today, and you said yesterday?
No, it was yesterday.
It was yesterday.
If there was one today, I don't know about it yet.
Any measure of roughly how much stuff is being thrown out during these outbursts? And isn't it typical that comets, as they are, this one's a few days away from perihelion, that they do become more active? Isn't that to be expected, or is there something really unusual going on here?
The overall activity of Temple 1 has been observed at several previous perihelion passages, and actually the overall activity peaks a couple of months before perihelion in Temple 1 at previous apparitions. And basically all the ground-based observations have shown that the activity is decreasing. And that means it's basically a seasonal effect. Where the outgassing comes from is coming into sunlight. You know, it's getting to be summertime, where the active part of the comet is. Some comets are more active after perihelion. Some are more active before perihelion. And so being active, peak activity right at perihelion is in fact not the normal case. It's our approximation averaging before and after. But in detail, they're actually quite different from that. What was the previous question? Oh. Well, as Jessica said, the biggest one doubled the amount of water in the coma. We haven't worked out the actual numbers yet. We'll have those next week.
I think we have a call. Do we have a caller? Okay. Okay. We'll take the call now.
Yes, this is Chuck Marble with KAZV Television in Modesto. First question is for Jessica. What will you consider the minimal objectives necessary for the encounter in order to call the mission a success?
Well, you're supposed to ask that question tonight. I'll give it a shot. I think we certainly want to hit the comet and watch what happens. And as Pete talked about, we're going to have some surprises, and that will be great.
Great. And Michael, are there any entirely new technologies on this spacecraft? Any scientific firsts on deep impact?
Entirely new.
The whole concept of hitting the comet is a first. That's entirely new. The high-resolution imager is new in the sense of being much bigger than any interplanetary instrument that's ever flown before. Although actually there will be a larger instrument going to Mars starting in August. So we won't be the largest one for long. Those are the two big things that are new. I can't think of other things that are entirely new.
Did you have a follow-up question? Okay. Any other questions here at JPL? Okay. We have Aviation Week.
Yeah, I'm not sure who wants to take this, but I assume that your assumptions of the size of 9 by 3 by 3 miles basically come from, first of all, Temple 1 I assume has never been resolved, and then that assumes an albedo to come up. No? How did you figure out what the size is, and what do you think the albedo is?
We get the sizes by measuring the thermal emission from the comet. We tried it first from Keck several years ago, had limited success, and did it again in the spring of 2000 using the Spitzer Observatory. The thermal emission is sensitive to the size and 1 minus the reflectivity, but comets are all fairly dark, so 1 minus the reflectivity is 0.9 or 1. So you get a size that's pretty much independent of the reflectivity. Then you combine that size with, for example, the observations we made with the Hubble Space Telescope, and that tells us the albedo, which is 4%.
Okay. Any other questions here? Okay. We have one from NHK. Let's get you the microphone.
Dr. Hearn, will the new understanding of the structure of the comet help us in evaluating strategies against possible catastrophic cometary impact to Earth?
Yes. In fact, if you are worried about defending the Earth from possible impactors, it's sure a lot easier to change the course of something if you know what it is you're changing the course of. You cannot design a sensible defense system without knowing what the impactors are.
Okay, any other questions? Okay, well, thank you for joining us today. Good afternoon, and thank you for joining us. I'm Natalie Godwin here at NASA's Jet Propulsion Laboratory in Pasadena, California. We're here for the latest update on the Deep Impact mission. Last night, we successfully separated the impactor spacecraft from the Flyby spacecraft, and now they're both flying to help scientists unlock the secrets of comets. Joining us today with more information on the separation, we have Andrew Dantzler, Solar System Division Director at NASA headquarters. Oh, not yet. Sorry. Rick Gramier, Deep Impact Project Manager here at JPL. Jennifer Rocca, Deep Impact Systems Engineer here at JPL. And Mike Ahern. He is the Principal Investigator at the University of Maryland. But first, I'd like to introduce the Director of JPL, Dr. Charles Alacci, for a few remarks.
And good afternoon, and I want to welcome all of you to NASA's Jet Propulsion Lab on this very historic day. You are witnessing with us one of the most daring and risky space missions that we have ever undertaken. Last night we successfully pulled the trigger, as was mentioned earlier, and you'll be hearing more about it, and the impactor is heading at 23,000 miles per hour toward the comet. Again, as I mentioned yesterday, at that speed you can go from LA to Washington in less than 6 minutes. So that gives you a feel about the speed we are moving at. So you will be witnessing tonight, for the first time ever, the unveiling of what comets' interiors are made of. So imagine that tomorrow our knowledge of our solar system would be different than what it is today. And a new trail would have been laid out for exploration that other people will follow, or next generation will follow in the future. Now, there are still high risks over the next 12 hours, but the Deep Impact, what I call the dream team of Deep Impact, has done everything possible to make it a success. So we are delighted you are here, and we are delighted that you are joining us on this great adventure of exploration.
Now we will hear from Andrew Dantzler.
Okay, I'm as ready as the spacecraft is. I'd like to emphasize just how quickly this mission has played out. In fact, just less than 6 months ago, NASA launched the Deep Impact spacecraft on their way to an encounter with Comet Tempel 1. And in those 6 months, as Dr. Alacci just mentioned, our dream team of scientists and engineers and technicians have worked tirelessly and diligently to make sure that everything is taken care of, the spacecraft are perfectly healthy and are where they're supposed to be. And I'm very happy to say at this point that that is the state of things. The Flyby spacecraft is ready, and the impactor spacecraft is where it's supposed to be, and everything looks green. I should remind you that Deep Impact is a mission in NASA's Discovery Program, and the goal of the Discovery Program is to provide opportunities to study the solar system, and so we can gain new insights into our solar system and learn more about the origins of our solar system as well as other solar systems that are out there. And Deep Impact is definitely in the spirit of the innovative, exciting missions that the Discovery Program does. If I could have the first video. This is what we hope to experience. Of course, there won't be a streaming video of the event, but from the Flyby spacecraft's point of view, We expect to see the impactor go into the comet, and we're not sure what happens after that. It should be a good-sized plume of comet interior, definitely a crater, but what deep impact does, we will find out in a short 12 hours. So, for this dramatic conclusion of this very exciting, cool mission, all the players in the right places, and at a spot 80 million miles away from us, the stage is set. So we're looking forward to see what happens just 12 hours from now. Rick?
Thanks, Andy. Good morning, everybody. What I'm going to do is provide an overview of what's occurred over the last 24 hours or so, and then I'll be followed by Jennifer, who will speak a little more in depth about what we still have left to do. So starting yesterday, probably, let's say about 36 hours before the scheduled impact, we were getting all the systems ready to perform our final targeting maneuver of the two mated spacecraft. We call this Trajectory Correction Maneuver 5. Give you an idea about how well we're doing, after traveling about a little over 200 million miles, this final targeting maneuver to release the impactor on its impact course was less than 1 mile per hour of adjustment. Now, what we did is ensure that all the systems on both spacecraft were healthy, because soon after the performance of the TCM-5, we would be transitioning the impactor to internal power and getting ready for the release. So we went through a poll of all the subsystems on each flight system and verified that all was nominal as expected, and performed the burn, which executed nominally and was within, I believe, about 0.4% of the expected design of the burn. This has been a well-behaved spacecraft, and all the burns have performed at less than 1% of error in the design value, so it's been very good. Following that, as I said, we then started transition and preparing for putting the impactor on its own internal power. So we performed polls to make sure that both the flyby and the impactor spacecraft were ready for that event, warmed up the batteries, and slowly began to transition power to the impactor. At that point, we took one final poll, determined everything was nominal, and gave the go to transition the impactor to its own power. That occurred nominally. We took another quick poll and made sure that all subsystems on the impactor were nominal based on running on its own power, which is the first time. It's basically battery powered. It's not solar powered as the flyby is. Now, if I could get the first animation, what we then did, as you can see here, we turned to the release attitude and then released the impactor on its impact trajectory. Right after that, the flyby, about 12 minutes later, the flyby began what we call its divert burn. Now, this burn is the largest burn that we've done on the system, designed to slow it down and place it in the right position to be able to watch the actual impact event itself. Now, this is quite challenging because both the spacecraft are operating on their own with their own auto navigation, and the flyby has to be pointed at the same target that the impactor picks out. So this is still quite a challenge. We did, not too long after that, verify that the impactor had in fact detumbled and slowed its rates down and turned on its S-band communication system, and we basically established communication with the impactor spacecraft, and it started flowing data through the flyby back down to the DSN network and into our MSA. As you saw at the end of that video, I may not have pointed it out too well, there was, you could see right after release and the divert burn, the flyby turned back, and actually you could see that the impactor was in its field of view. That was our plan. I'm happy to report that that plan worked out very well. If I could have the next picture. This is a picture, imagine this, we've just completed the largest burn on the flyby.
and we've turned back and captured the impactor on its course right after that burn. So this is a very good indication of how well this system is performing, just absolutely phenomenal. So that's how it looked from space in the flyby spacecraft. If I could have the next roll, you'll see that once we got confirmation in the MSA area that everything was nominal and we had established contact with the impactor spacecraft, there was quite a bit of excitement, as you can see here. We were all holding our breath for that event. So another challenge out of the way. Back up in space, we're now on our course. We have validated that the impactor is on its trajectory within less than a kilometer, which is absolutely phenomenal from a navigation viewpoint. And we have also established that the flyby is also less than a kilometer from its aim point. So now to tell you a little more about what you can expect in the next few hours, I'll turn it over to Jennifer.
Thank you, Rick. As I'm sure you can imagine, we have quite a night ahead of us, and we're very excited and refreshed after a few hours of sleep to get ready for the big events this evening. After successful separation of the spacecraft and the divert maneuver of the flyby and impactor are beginning their independent missions for the encounter phase. I'm going to talk first about how the flyby and impactor work together, even though they're separated, and then I'll speak a little bit about what the impactor will be doing and then also what the flyby will be doing. Both spacecraft, when they're separated, communicate via S-band, and Rick talked about how we checked out the S-band system after separation. It's working absolutely nominally. The spacecraft communicate in a way that's similar to a space game of telephone. The impactor spacecraft is not strong enough to communicate with Earth directly, and so all of its data and images are sent across to the flyby, which in turn sends its data, images, and the data from the impactor on down to the Earth. We're supported by the Deep Space Network, of course, during this time. We have continuous 70-meter antenna coverage, which allows us to monitor everything that goes on the spacecraft around the clock. Our ground antenna coverage is, of course, extremely important during the final encounter events, and so we have actually triple coverage during this time. We have two 70-meter antennas. In addition, we have a 4-station 34-meter array, which approximates the performance of a 70-meter station, giving us triple coverage. For the exciting events that unfold this evening, Deep Impact uses a strategy called Live for the Moment. We take many, many images throughout our campaigns on both spacecraft. To the flight team, the Live for the Moment strategy means that we take the highest priority images. The high priority images are defined by science, of course, and we transmit those to the ground first. This means as soon as the high priority images are taken, they're sent to the ground. Our attempt is to get all of these high priority images down to the ground prior to the flyby reaching its closest approach to the comet. This means that even if the flyby spacecraft suffers damage during its closest approach, we will preserve our best science data. The impactor spacecraft on its own, of course, went through detumble and rate capture, and that was performed successfully, allowing us to communicate with the spacecraft as planned. The separation from the flyby kicked off a sequence on the impactor spacecraft, not unlike launch, kicked off a sequence on the flyby, and this sequence has many images throughout its campaign. It's imaging all along the way and sending these images over to the flyby and then down to the ground. And the imaging campaign allows the impactor to start getting a look at the comet and prepares us for our final targeting maneuvers. And if you'll show the first clip. This is the impactor on its own. It does autonomous navigation, and you can see it firing its thrusters there. It does 3 course correction maneuvers on its way into the comet. The first one at 90 minutes prior to impact, the second one at 35 minutes prior to impact, and the final one at 12.5 minutes prior to impact. These maneuvers are calculated autonomously on board. The one-way light time at this time is 7.5 minutes. That means that it takes 7 minutes, more than 7 minutes from the time we send a command from the ground until it gets up to the spacecraft. The autonomous navigation system on the impactor is ready to go. We're happy to start looking at the pictures as the comet gets bigger in the field of view. And we anticipate a little bit of a rough ride. We know that there will be a debris field as we get closer to the comet, but we are taking pictures all the way in. We can get pictures from the ITS as late as 3 seconds before impact, and as long as no debris goes into our camera, they should be pretty outstanding shots, so we're anticipating that. On the Flyby spacecraft, of course, we released the impactor onto an impact trajectory and then performed the divert maneuver, putting us in line to take pictures of the impact when we get to that time. It also is continuing with its imaging campaign with more instruments on the Flyby. Of course, that imaging campaign is more intense than it is on the impactor, and we are using every single bit of bandwidth that we have to downlink those images to the ground. This imaging campaign continues all the way up until the impact event, and of course some of our very highest priority images are those taken of the crater as the impactor hits. And of course as the crater develops as we go. And if you'll show the next clip, please. This is the point of impact, and you can see that the crater will be developing and we'll see the ejecta coming out. These are some pretty outstanding pictures we're really looking forward to from the Flyby spacecraft. We have 13 minutes from the time of impact while the Flyby can still look at the crater, and then the Flyby continues to look toward the comet as it can. It turns into shield mode to put our safe shield area toward the dust flow and protect our spacecraft as we fly very close to the comet. And then after that, we do our final look-back imaging, which means flew back toward the departing comet and taking pictures as the nucleus departs. We continue these look-back playback cycles for 60 hours. We take many, many pictures of the comet. We have to do this on our low-gain antenna because the attitude does not permit us to use the high-gain antenna. Then we flew back, downlink all those images via high-gain antenna, and then turn back again to do another look-back cycle. It's an understatement to say that the flight team is excited. We are so proud of everything we've accomplished over the last several hours. We are very confident and very anxious to see the performance of the event in the last hours. We are ready and very, very, very excited to see thrilling images of Temple 1 and the Deep Impact Crater. With that, I will pass it over to our principal investigator, Dr. Ahern, who will tell you more about the science.
Thanks, Jen. I'll tell you just a couple of highlights of what Andy, Rick, and Jen and the rest of the team have made possible. You've all heard that there have been outbursts by the comet. These were not expected. They hadn't ever been observed from this comet on the ground. They're observed from others. We've now been working to understand what drives those outbursts, and the first still image shows a spectrum, one of those funny squiggly lines that nobody can understand. Basically, it's the amount of light at every different color in the infrared. And that spot in the middle is all light from water molecules. And what we've done is combined a whole bunch of these squiggly lines to actually make a picture of the comet in the water molecules only, and that's the next still. There's 4 pictures of the comet in the water molecule. The first 2 images in the upper left are before one of the outbursts. The third one was near the peak of the outburst, and all the water is at the middle. And then the one in the lower right is a couple of hours later, and you see that the water has spread out. Now what we're working on is trying to understand whether that water came out mostly as water vapor, like the humidity in this room, or mostly as ice crystals that then vaporized when they spread out. And that's what we're trying to separate out now. So that was just one of the outbursts. I'll also show you how much the comet is growing as we approach it. This is a movie of the comet as seen with the MRI image instrument, the medium resolution imager, over a period of a month. Getting closer, and you'll see a couple of outbursts. It actually ends right at the last outburst. There was one of the outbursts. That was a jet coming out this way towards you mainly, and a little going to both sides, so it looked like shooting out in both directions to the side. It was really coming this way. Now, what's going to happen tonight? We're going to get tremendous data from the spacecraft, and you heard about that already from Rick and Jen. And we're also going to get a tremendous amount of data from many dozens of other observing facilities. The next still is a picture taken yesterday from the Chandra orbiting X-ray telescope. And that bright green area is sort of medium energy X-rays right near the center of the comet. fact that they're right at the center of the comet tells us there's not much gas coming out of the comet. It's interacting with the solar wind. Most comets, you see that arc of X-rays way up on the sunward side, not right at the center. What we expect will happen, for example, is that after the outburst, we'll put a lot more material in the coma, and that X-ray region will move out towards the sun. But that's just one of, as I said, many dozens of facilities all the way around the world, which are all collaborating because we couldn't possibly build a single flyby spacecraft that could carry every kind of instrument you'd want to measure what happens during this spectacular impact. Thanks.
We'll take questions here at JPL. Any questions? Okay, let's wait. Let's get a microphone over here. We will start with Aviation Week. Right here. In the second round.
Yeah, could you put a quantity on the brightest of these outbursts compared to the nucleus intensity?
Brightest, total brightness of the outburst is several tens of percent of the nucleus, 50% maybe, ballpark, to the best we've looked at the data so far. But that rapidly dissipates. They all dissipate within an hour. They're entirely gone.
Okay. And I would like to have a note for the media. Please say your name and your media organization. Okay? And we're going to go right here.
Katie Human with the Denver Post. Do you guys have a sense yet how long it'll take you to deconvolve those first high-resolution images of the crater?
I'll say 2 days so that I don't get nailed if we don't have them out in 6 hours.
Okay. We're going to, right here, CBS.
Bill Horowitz, CBS. Just another picture question. As you move in tonight, approaching the comet, the impact, and then receding, what is how are the images that come in going to be released? What are we going to see as the night progresses? When will you get close enough to where even the medium resolution imager or whatever we're seeing will show things that are obvious to a non-scientist that this is a comet and recognizable as such? How are we going to see all this stuff?
Well, I'll tell you when we'll see it. You won't see a recognizable nucleus in the medium resolution image, and those are the primary ones that are being released just because the high resolution images have to be deconvolved. You won't see something that's recognizably an obvious comet nucleus until an hour or two out.
Will those be released over the web or over the TV as you guys are playing the night out?
All the medium resolution images, until we stop real-time playback to do the look back, they'll all be released both on the web and on NASA TV.
Okay. New Scientist, right here.
A little bit more about the images that we can expect. We've been looking at these wonderful artists' conceptions of what's going to happen with incredible levels of detail. You see every little particle flying out and so forth. Can you give us some sort of qualitative sense of what we're really going to be able to see in the best of the images compared to, seeing so much detail? Is there any possibility that we'll actually be able to see the crater in the images, for example? And how much detail will there be?
Well, this of course depends on how comets work, and we don't know that, which is why we're doing the experiment. But if they work according to our favored scenario, and you get a really big crater, if the material is like soil on Earth or like sand or anything like that, then you get the really big crater, and you'll be able to see the crater as a crater even in the MRI images quite clearly. What you see in the ejecta cone, it may be just fine material, in which case it looks like a smooth continuum. If there's a crust near the surface, we'll probably break off much larger chunks, and you'll see those as the individual pieces, more like what you saw in that simulation.
Let me ask one follow-up. You're talking about all these outbursts we've been seeing lately. If there should happen to be another outburst close to the time of the impact, what effect might that have on your observations? Could that cause confusion as to what's coming from the impact itself and what's just an outburst of the comet?
Fortunately, they dissipate so rapidly that AutoNav can recover from any confusion. But I don't think it will be a problem. It turns out that several of the outbursts seem to have occurred at the same point in the rotation of the comet. Not all of them, but 3 out of the 4 that we've observed all seem to have occurred at the same point in the rotation. So it's probably a single area. Doesn't even happen every rotation, but it's the same part of the rotation. And if that one goes off again, that is something like 4 to 6 hours before the impact, so that's before AutoNav, when the impactor starts working. That really starts working 2 hours out to do that maneuver at 90 minutes.
Okay, right there. Yes.
Todd Neff from the Daily Camera in Boulder, Colorado. Do we have an exact idea of the size and shape of the comet, and when will we have that notion?
We'll have a great idea tomorrow. No, we know roughly the size, and that's about all we know. We know it's elongated. We know roughly the size. The standard quoted numbers are 4 by 12 kilometers or something like that.
Okay. Washington Post.
Yes, probably for Rick, Guy Guglielmo from the Washington Post. Can you describe in a little bit of detail the pattern of commands, how the impactor moves, how it sends the commands back, or how it describes its actions to the Flyby spacecraft? And are you going to be able to download all of this, all of what's happening later on, so you know exactly how this unfolds?
Sure, I'll take a stab at that. Basically, the impactor is running on what we call the critical sequence engine, and basically this is a series of commands that have already been tested and uploaded to the impactor spacecraft. It does not involve real-time intervention from the ground. Those commands clock out on a periodic basis based on the timing that we've set and tested, and tells it to do such things such as take a ITS image here, take one there, take them with these exposure settings. Based on attitude control feedback, it also makes sure that it stays within its dead banding rates. Then at 2 hours out, it is commanded to start its AutoNav processing. So all this is basically automated on board. Now, the data itself, which we call the telemetry, it reports back to the Flyby spacecraft based on a scheme that we have given it that says take these pieces of data and report them back at these particular intervals in time. So it's cyclical. And then the Flyby spacecraft forwards those down to the ground. Now, obviously, that data can be used for reconstruction, and in fact, we're using the OpNav data to make sure that we've got a good fix on where it is. So as much data as we transmit across, most of that is science, and some of that is engineering.
Okay.
So then, how often are you getting sort of a fix on the situation at this point?
A fix from the viewpoint of its location, or its...
Yeah, its location and how everything is functioning.
Ah, okay. Well, we're constantly getting telemetry down. Okay, so every hour we ask the attitude control folks to give us a status report on how it's behaving from an attitude control viewpoint. Every 2 hours we get an optical nav solution on where it is. So we keep in touch with it quite a bit.
Okay. We have Fox News.
Hi, Nora Zamet with Fox News. Can you explain what kinds of questions you think this mission is going to answer about our solar system? Dr. Alacci was talking about the idea of water in our solar system, how this mission may help to understand that in organic matter in our universe.
A lot of scientists think that most of the water, organic material on Earth came originally from comets roughly 4 billion years ago, when the late stage of everything falling on the Earth and on the Moon, where you still see the cratering record that showed this huge surge of bombardment 4 billion years ago. Part of it was asteroids, part of it was comets. And we really want to know what those materials were, because the conditions that the planets formed under are not really well determined yet. And the ices inside the comet nucleus are very sensitive to the temperature at which the early pieces of the planets formed in the outer solar system. So what we want to do is understand how the inside of the comet is different from what we see from the ground, and then we can use all the wealth of Earth-based data that we have on comets to say what the interiors are of all those comets, and therefore put limits on how the planets formed. And that in turn will then allow us to understand what came to Earth in the early solar system from comets, and sort out whether in fact we are all comets, or maybe we're partly asteroids.
Okay, Kim with KTLA?
Yes, I'm Kim Murgy with KTLA News. If people in Southern California were to use a telescope and look in the sky at the exact time of impact, 10:52, what should they expect to see?
Well, I'll take a shot, and then you can correct me if I'm wrong. He needs a break here. That's another question that doesn't have an exact answer. Obviously, there will be a momentary flash, but we think that'll be pretty brief. What we do expect is, depending on the type of crater that's formed and the amount of material that is thrown up, that you could see a brightening of the comet for a few hours to several days.
And where in the sky would they look?
Southwest, around Jupiter, and I forget the constellation.
In the constellation of Virgo.
There you go.
Yeah. Forms a nice triangle with Jupiter and the star Spica, a couple of degrees away in the sky.
Okay, thank you.
We're going to go on this side. The gentleman in the blue shirt. Please wait. Hold on. Please wait for my microphone.
I'm Bruce Lieberman of the San Diego Union Tribune. Can you give us a sense of what images the spacecraft are taking right now of the comet, and at what point the spacecraft will be able to delineate the nucleus from the coma? And when those images will be coming in prior to impact?
We started separating the light of the nucleus from the light of the coma 2 weeks ago. It was still a point source, but you could separate which light was coming from the nucleus and which was coming from the coma. So we've been doing that for the last couple of weeks already. We have some images from this morning with the high-resolution image that, after deconvolution, suggests that we're beginning to spatially resolve the nucleus. But you wouldn't believe it if I showed it to you, but I believe it. So we'll start to see resolved images, spatially resolved images, I think, if we keep working hard at the deconvolution, the next few hours.
Okay. We have Jim Erickson right here in the second row. Right here.
Jim Erickson from the Rocky Mountain News. What is the approximate current distance of the spacecraft from the comet? Is the impact time still expected to be 10:52? Has that changed at all? And how long after that impact will you be able to say whether things worked out or not?
Currently we are about 225,000 miles. We're 12 hours out, and we move about 550,000 miles a day. So, so that's where we're at.
Is it still 10:52, the expected?
As far as we know, the impact time hasn't changed.
And how soon after that will you be able to say whether things worked out or not?
We're basically looking at anywhere from 20 minutes to 45 minutes or so, depending on the data we get down and the analysis of the pictures.
And one little follow-up. What is it that exactly tells you if it worked or not? Is it you get the loss of signal from the impact, or you get flashes in the telescopes on the flyby, or how do you know that it hit?
Well, that's a good question, but basically we're going to do it based on the images that we get back from the flyby, plus some of the last images that we get back from the impactor, assuming that we still get good images within the 30 seconds prior to impact. We don't consider loss of the S-band signal to be a sufficient condition to declare impact, because that can be affected by geometry or just by the dust particles that it's running into, etc. So it will require getting the getting the impact and post-impact images back down and doing a quick analysis of those to determine that we had a hit. Now, if in the meantime we get a report from one of the observatories, obviously that'll help resolve that.
Okay, right here. I have a question here.
After those first 12 minutes, Katie Human, Denver Post. After those first 12 or 15 minutes, how long is the flyby going to spend in the coma? And do you guys have any updated information on whether your initial models of the debris in that region were correct, or if the flyby is likely to encounter bigger particles?
Okay, I don't know the exact exit from shield mode.
We start look-back imaging at 40 minutes after impact. So we're sufficiently far away that we can turn back and look at the nucleus at that time.
And we have no indication right now as far as the quantity and size of particles versus what we've modeled.
And one more, the image that you guys shot with the flyby of the impactor, what was responsible for that brightness? Was that sunlight reflecting off of the back of the impactor?
Yes.
Is that copper, or is the back of it another material?
It's actually our S-band antenna material.
Which is?
I don't know what that is.
It's probably thermal blanket stuff, you know, shiny like.
I couldn't tell you right off the top of my head.
We have a follow-up with PBS.
Bill Harwood, one more time. I should know this, but I got confused last night reading various materials. When you release is it currently on an impact trajectory, or does it require the TCMs to put on an impact trajectory?
The impactor you're asking about? It's on an impact trajectory with an error right now of, like I said, less than a kilometer. But obviously it's going to require adjustments as it goes in, and that's why we have planned the 3 maneuvers that we have targeted for it.
It's Comet, no matter what, unless it's...
Well, we still haven't, I mean, there's still uncertainty in the Comet ephemeris, so you can't say it's exactly going to be a hit. You got to adjust to that as you get closer. Remember, it's just very tiny right now in the targeting system.
Okay. Fox News, and in the back, please wait for the microphone.
You talk about adjustments. Adam Housley with Fox News. You talk about adjustments. One of the curiosities we were talking about this morning before you guys sat down was looking at the spacecrafts even around here, the models of them. You don't know what's on the perimeter coming towards the impactor. What are some of the troubleshooting measures you took or that were taken to help this impactor basically deal with anything it might encounter as it comes towards the comet? Does that make sense? I mean, is it going to be, for example, a piece of, not space junk, but something was to hit it or come near? What are some of the things you've done to troubleshoot to help keep this impactor on target, in layman's terms?
Okay.
In other words, give us something we can... I'm joking.
That's fine. Well, the attitude control system and the reaction control system are designed such that they could take some of the predicted particle hits that will turn it around or set it off course or whatever. It's got a certain band that will operate and bring that back in without having to you know, think that hard about it, I guess is the best way to put it in layman's terms. And then the autonav system itself is always keeping the comet and the nucleus and it's as a center of brightness in its targeting system, and that's what it operates on. And that, as it gets closer, will dominate the field of view. Okay.
Okay. Well, let's go to the Pasadena Star News.
Hi, Kim Grosham from the Pasadena Star News. I'm just wondering, this is kind of maybe a bit too far out, but originally there was some talk of the Flyby spacecraft eventually possibly going for another comet, looking at another comet in the future. Is that still on the table, or is that completely scrapped at this point?
Well, we're looking at all the options for the flyby spacecraft. The Deep Impact was funded as a competitively selected mission to do exactly what you've been hearing is described. What happens after that is another mission. And so we have to look at the funding levels, possible proposals for what we can do with it. But so the quick answer is the flyby spacecraft, as long as it stays healthy, is out there to be used, but we don't have a definite mission set for that.
Okay.
Sam Chulin with KTTV Fox 11 News, Los Angeles. This mission apparently looks like it's been running very smoothly, but is there a singular major challenge that you scientists have had to face, or challenges?
Making a comment.
Well, I think we still have our biggest challenges to go, which are basically we're going to a body in the solar system that we haven't even resolved yet from a spatial viewpoint. I'm sure it still holds a lot of surprises for us. We still have yet to perform the actual auto navigation on the impactor flight system itself. That doesn't cut in until 2 hours out. We're still watching the performance converge on the attitude control system and observing that. So we've still got quite a few challenges left to go. Now, having said that, you still have to have the flyby spacecraft operating on the identical targeting algorithms to be able to look and see that impact occur. And that's also dependent on what the shape of the comet nucleus is, because it could, we think it's misshapen, and if we target a certain point, we're trying to target a lit portion of that nucleus. But if there's a geographical feature that could possibly block the flyby from seeing that, that's another issue we have to deal with. So there's all sorts of challenges still out there to meet.
Okay. New scientist? Yeah.
David Chandler from New Scientist. Well, let me just quickly follow up on that. Of all those challenges between now and the moment of impact, or between getting your data back, is there one that sort of looms as the sort of biggest hurdle to get past, or one thing that worries people the most?
I don't think there's anything other than what we probably said. I believe Dr. Ahern's primary concern is that the flyby is actually pointing at the impact site and captures the crater. That is a big challenge. Otherwise, all our systems are nominal and are performing very well. So really, it's up to the auto navigation and the comet itself. That's really where we are.
And we don't want a mountain between us and the crater. We have no control over that.
Okay. We have a question all the way on this side over here. I know you've been waiting. We'll get a microphone to you.
Martin Kemp, BBC Television. How soon after the impact do you think you'll be able to tell us what type of crater it is and what that might mean for the composition of the planet, of the comet sun?
I hope we'll be able to tell you at the press briefing tomorrow morning. Late morning, not the 1 a.m. one, the 11 a.m. one. I am not prepared to be awake enough at the 1 a.m. one to tell you what kind of a crater it is. That's just going to require a lot of discussion on the science team.
Okay. And we're going to come back to the front. We have Aviation Week. It's coming to you this side.
Aviation Week. My sense is, first of all, that neither of the spacecraft have any sort of hit counter on them. Is that correct? Okay. Given that you might want to, develop a spacecraft down the road, it would be sort of useful to know what the field is. And is there a reason that there is no hit counter on there? Could you just go into? Was that considered at all in the design of the spacecraft?
Well, I couldn't answer if it was originally considered or not. The way I can answer it is that the Discovery missions are very focused and typically are very limited on the science instruments for very focused science. And even though that is not on there, that obviously was on the Stardust spacecraft that flew through the Welt 2 coma. So there is data on the particle flux and distribution from that viewpoint.
My impression is this was originally a faster, better, cheaper program. Is that right? And could you...
No, the Discovery missions are all, the goal is to, as I said, study the solar system, but for a relatively low investment, frequently flown missions, try to fly them less than every 2 years. So it's not faster, better, cheaper in that sense. It's cheaper in that it's designed for the $300 to $400 million class of mission.
Yeah. Well, let me, over the evolution of the mission, how has the risk level changed, or what have there been additional resources put into the mission since it was first conceived to address risk? Was there an altered perception of risk that occurred during the development of the mission?
Most definitely. As you start out with a design and a concept, as the scientists say, okay, this is we're simply recreating an experiment that naturally occurs in space, only we're going to do it with a man-made impactor. When you take that idea and start putting it on the drawing board and really thinking and bringing it to engineering fruition, so to speak, you do run into issues that you hadn't anticipated on before, and you have to work those in order to make it a definite success. As you can see from the orchestration that this requires of 2 different spacecraft, which are different. These aren't identical spacecraft. It's much more complicated than it was probably originally thought it was. And we've taken additional steps and extra steps with the help of NASA headquarters to ensure that we've knocked down the additional risks that we've uncovered as we've gone along. And we have really tested and poked at this thing from several different aspects. We did a lot of simulations and tests that poked at the boundaries to see where the parameters were that needed to be adjusted that affect us the most in our performance in the cometary environment.
Okay, and final, could you just give an example of 1 or 2 of those cases where you had to change the parameters, where risk was found and you put extra effort, money at it?
Sure. Attitude control system and the attitude convergence and how the star tracker interacted with that required that we take additional steps and do additional testing more than anything in order to make sure that we had it down, those rates down low enough so that the autonav could perform. And then that also required additional modeling, and not just one Comet model. We had to have several Comet models that we tested against.
Any other questions here? Okay. Anyone here?
My understanding is that the mission went from originally being proposed at about $250 million to today's estimate of $333. Is it that those risk reduction and extra testing programs that are responsible for the increase in cost?
That's, you could say that. That's part of it. There was a delay. We were going to launch a year before we did. Bear in mind that, as Dr. Alacci opened up with, this is a very daring, difficult mission, and it is certainly worth the additional money and additional time to make sure we get it right. As we've all tried to emphasize, there's no guarantee of total mission success here. However, the team has done everything they can to reduce the risk. This has been a very interesting mission in that, unlike many of the missions that we do, there's been an awful lot of learning as we go, learning after launch. The trajectory is all set, but as Rick was mentioning, as we approach the comet, we know the rotation rate of other bodies we visited. We didn't know the rotation rate of this comet, for example. So making sure we've reduced the risk to the point where we reasonably can expect success was certainly worth the effort and the money.
Okay. And back to the question about tense moments last night in mission control, it looked like there was a moment when you guys were late in receiving word back from the impactor. Can you tell us what you know now about why that happened and what was going on up there?
I wouldn't call 30 seconds overly late, particularly with the one-way light time. I mean, we had to predict that the S-band would lock up and begin sending data to the flyby. It takes a while to get it to that part of the pipe and then get it back down to the ground. So 30 seconds, I think that's not bad at all.
And one last question from New Scientist. That's right beside you.
Yeah, I guess this is for Micah Hearn. Can you give us a sense of the sort of expectations among the science team? You've described the sort of range of possibilities of how big the crater might be and what the effects might be, but are there particular members of the team who have specific models or specific expectations at one extreme or the other of that range? Do you have a pool going among the team on how big it's going to be? What's the sort of range of thinking on the team?
There is a pool. I'm not the custodian of the pool, so I don't know what the range of bets is. However, none of us, I think, really expects either of the true extremes. You know, one extreme being tunneling in with a really narrow, deep crater. I don't think any of us really expect that. There are ways it could happen, but we don't expect it. At the other extreme, you go in, you make the crater, and the comet then undergoes enough reactions and release, and ice is vaporizing, highly volatile materials vaporizing, and just pushing itself apart. Again, so those are what I view as the extremes, and I don't think any of us realistically believes either of those extremes.
Okay, we have really one last question.
I assume scientists and astronomers worldwide will be watching what you guys are doing in the next 24 hours. And since this is a international kind of story, would you reiterate for us how you hope to disseminate this news and get that active participation of those astronomers, those scientists, so they can get this information quickly?
We have a private email network that goes to collaborating observers at essentially every observatory in the world. Every major observatory is participating. So as soon as there are results, we tell them what we're seeing, they tell us what they're seeing, mostly by email. We're also doing it by Polycom, managed by Karen Meach, who's on the science team. She's resident in Hawaii, which is the prime site for observing the event, and she's coordinating the entire Earth-based program. So she's the one that's basically talking to everybody. She's not observing herself. She's just talking to every other observer. Yeah.
How many people are you talking about?
I would have to say 150, 200. A few per telescope. Something over 50 telescopes. It doesn't include all the support staff at the observatories, but the actual scientists.
Okay. Unfortunately, we are out of time.
Innerhalb einer guten Woche ist jetzt zum 3. Mal ein Schwimmer von einem Hai angegriffen worden. Das jüngste Opfer stammt aus Österreich. Mehr von Alexander Römer.
Der 19-jährige Armin Troja hatte Glück im Unglück. Der Hai erfasste lediglich sein rechtes Bein. Der junge Österreicher badete im brusthohen Wasser nur 50 Meter vom Strand entfernt. Daher konnte sich Armin an das Ufer retten. Helfer versorgten ihn. Mit dem Helikopter ging es sofort in das nahegelegene Lee Memorial Hospital. Armin Troja wurde sofort behandelt. Seine schweren Fleischwunden konnten gut versorgt werden. Der Österreicher kam glimpflich davon und wird wahrscheinlich keine Langzeitschäden zu beklagen haben. Tragischer das Schicksal der 14 Jahre alten Jamie. Sie musste wenige Tage zuvor ihren Badeausflug mit dem Leben bezahlen. Und auch der 16-jährige Craig hatte weniger Glück. Er verlor beim Fischen auf einer Sandbank sein rechtes Bein durch einen Haiangriff. Experten schreiben die Angriffe Bullenhaien zu. Diese können bis zu 3,5 Meter groß und bis zu 200 Kilogramm schwer werden. Bullenhaie sind berüchtigt für die Jagd in Flussmündungen, da sie auch im Süßwasser nach Beute suchen. Mit Kontrollflügen will die Küstenwache die Bullenhaie nun vermehrt beobachten. Die Strandpatrouillen wurden ebenso verstärkt.
Vielleicht erinnern Sie sich an den Kino-Endzeit-Stimmungsfilm Deep Impact. Ein Meteorit schlägt auf der Erde ein und die Folgen sind verheerend. Die NASA testet jetzt genau solch einen Einschlag und auch seine Auswirkungen real im Weltall. Aus einer Sonde wird ein Komet beschossen. Auch diese Mission heißt Deep Impact und keine Sorge, es geschieht weit genug weg. Miklocher.
Ein Geschoss groß wie ein Kühlschrank im Anflug auf den Kometen Tempel 1, 130 Millionen Kilometer entfernt von der Erde. Es geht direkt auf Kollisionskurs mit dem kosmischen Vagabunden von der Größe Manhattans. Der Einschlag erfolgt mit 40.000 Stundenkilometern. Mit der Wucht von 5 Tonnen Sprengstoff soll ein Krater so groß wie ein Stadion entstehen. Es wird ganz wichtig für die Mission sein, ob und wie tief sich ein Krater nach dem Einschlag bildet. Die reflektierenden Sonnenstrahlen erhellen die aufgewirbelte Materie zunächst, bis sich die Trümmer im Weltraum zerstreuen oder wieder auf den Kometen zurückfallen. Die Wissenschaftler werden die Trümmer analysieren und hoffen auf spannende Bilder. Komet und Projektil werden dabei von der Muttersonde gefilmt, dann werden die Aufnahmen beinahe in Echtzeit zur Erde gefunkt. Gespannte Erwartungen bei der NASA. Zunächst werden wir vermutlich einen Blitz sehen, dann einen Rauchpilz aus Gas, der vom Kometen aufsteigt. Am 12. Januar war die Sonde gestartet, um zum Unabhängigkeitstag der USA am 4. Juli ihr Ziel zu treffen. Lediert, aber nur minimal aus der Bahn geworfen, wird Tempel 1 nach dem Treffer weiter seine Runden zwischen Mars und Jupiter ziehen. Der Beschuss soll auch klären, ob man einen Kometen zerstören kann, falls er unserer Erde zu nahe kommt.
Der Aufprall ist für Montagmorgen um 7:52 Uhr geplant. Dabei wird in den Kometen ein Krater von der Größe eines Fußballstadions gerissen. Aufsteigende Gase und Materie sollen den Wissenschaftlern Hinweise auf die Zusammensetzung des Himmelskörpers geben.
In diesen Tagen in Florida im Meer badet, der tut das wahrscheinlich mit einem ziemlich mulmigen Gefühl. Denn zum 3. Mal innerhalb einer Woche wurde dort ein Jugendlicher von einem Hai angegriffen, ein 19-jähriger Österreicher. Zuvor hatte ein Hai eine 14-jährige getötet, wenig später verlor ein 16-jähriger bei einer Attacke ein Bein. Aus den USA berichtet Volker Albers.
In diesem Helikopter wurde der 19-jährige Österreicher ins Krankenhaus geflogen. Es dürfte wohl der Schock seines Lebens gewesen sein, als der junge Mann im brusttiefen Wasser schwimmend von dem Hai ins rechte Fußgelenk gebissen wurde. Plötzlich packte ihn etwas am Bein, dann merkte er, dass er stark blutete. Und er schwamm so schnell wie er nur eben konnte, zurück ans rettende Ufer. Der junge Mann hat Glück im Unglück, die Wunden sind nicht zu tief. Ein paar Narben, das wird alles sein, was ihn an diese Haiattacke erinnern wird. Langsam wird man nervös in Florida. Der 3. Angriff dieser Art in einer Woche und alle an der Westküste. Erst in Miramar Beach, dann vor Cape San Blas und jetzt in Boca Grande. Das ist nicht nur ungewöhnlich, das könnte auch Touristen vergraulen. Letzten Montag hat ein Hai einen 16-jährigen Jungen angefallen, der im hüfthohen Wasser fischte. Er überlebte schwer verletzt, ihm musste ein Bein amputiert werden. Und vergangenen Samstag wurde dieses 14-jährige Mädchen von einem Hai getötet. Sie war auf einer Luftmatratze aufs Meer hinausgeschwommen, als sie von dem Raubfisch in die Tiefe gerissen wurde. Immer wieder nähern sich Haie auf der Jagd nach Beutefischen der Küste Floridas. Aber eine solche Häufung von Attacken auf Menschen ist eher ungewöhnlich. Jetzt überwacht man die Küste aus der Luft, sichtet man Haie, wird Alarm geschlagen. Die ersten Strände wurden bereits geschlossen, vorübergehend. Das Letzte, was man hier in Florida braucht, ist eine Haipanik, erst recht nicht am Anfang der Urlaubssaison.
Wir wissen ja, dass es in Hollywood genügend Helden gibt und so gehen diese dramatischen Filme immer gut aus. Den Titel von Spielbergs Film hat sich die amerikanische Weltraumbehörde NASA für ein besonderes Forschungsprojekt ausgeliehen, denn morgen früh lässt sie ein Kupfergeschoss mit einem Kometen zusammenstoßen. Ulrich Adrian über diesen Deep Impact.
Vor 7 Jahren bedrohte in dem Hollywood-Film Deep Impact tiefer Einschlag ein Komet die Erde. Seit Januar läuft unter demselben Namen eine Weltraummission der NASA, die das Wissen über unser Sonnensystem auf den Kopf stellen soll. Mitte Januar startete in Florida die Raumsonde Deep Impact. Seitdem flog sie 431 Millionen Kilometer durch den Weltraum. Ihr Ziel, ein ungefähr 50 Quadratkilometer großer Komet namens Tempel 1, der bereits 1867 entdeckt wurde und sich auf einer Umlaufbahn zwischen Mars und Jupiter bewegt. Von der Sonde aus gelangen diese Schwarz-Weiß-Bilder des Kometen. Heute Morgen um exakt 8:07 Uhr deutscher Zeit hat sich von der Sonde ein 370 Kilogramm schweres Kupfergeschoss gelöst. Großer Jubel in Pasadena bei der NASA, Erleichterung, dass das schwierige Manöver geklappt hat. In wenigen Stunden soll das kühlschrankgroße Geschoss auf Tempel 1 aufprallen und dabei pünktlich zum amerikanischen Nationalfeiertag am 4. Juli ein gigantisches Feuerwerk auslösen. Stellen Sie sich vor, dass das Wissen über unser Sonnensystem sich morgen völlig verändert hat zu dem von heute. Der Krater von der Größe eines Fußballstadions und die riesige Staub- und Gaswolke wird neue Rückschlüsse auf die Entstehung unseres Sonnensystems geben. Die Erde übrigens, da beruhigt die NASA, ist nicht in Gefahr. Das ist so, als wenn eine Mücke eine Boeing 767 rammt.